Time is supposed to erase things. It destroys wood, crumbles stone, buries cities, and wipes entire civilizations from memory. Yet scattered across the world are places that seem to have resisted that process. Massive walls still stand. Hidden chambers remain sealed. Ancient landscapes preserve traces of decisions made thousands of years ago. What is remarkable is not simply that these places survived, but that many of them remain difficult to explain. We know they exist. We can walk through them, scan them, and study them. But some of the most important questions remain unanswered. Who built them? Why were they placed there? What knowledge made them possible? The ancient world is full of discoveries that survived the passage of time, but not the loss of understanding. And that is where the mystery begins. Port Einon, Gower Peninsula, South Wales. Beside a windswept bay facing the Atlantic Ocean stand the remains of a small stone structure known as the Port Einon Salt House. At first glance, it appears insignificant compared to castles, cathedrals, or ancient monuments. Yet hidden within these ruined walls is a technological mystery that continues to puzzle historians today. How did a small coastal operation produce large quantities of salt in a cold climate while consuming far less fuel than modern calculations suggest should have been possible? The surviving structure was identified as a historic salt production facility through archaeological investigations, historical records, and the discovery of industrial features associated with salt boiling. Excavations revealed evidence of furnaces, evaporation areas, and specialized construction designed for long-term operation in an aggressive marine environment. What researchers expected to find was a simple medieval workshop. What they discovered instead was evidence of surprisingly sophisticated engineering. Of all the unanswered questions surrounding Port Einon Salt House, none is more fascinating than the mystery of its production efficiency. Salt may appear simple, but producing it from seawater is an extremely energy-intensive process. Modern seawater contains approximately 35 grams of dissolved salt per litre. This means that producing a single metric ton of salt requires processing roughly 28 to 30 cubic meters of seawater. In practical terms, more than 28,000 litres of water must be evaporated. The problem becomes even more difficult in Wales. Unlike the Mediterranean, South Wales experiences frequent cloud cover, lower average temperatures, and significantly less solar evaporation. These conditions make traditional solar salt production inefficient. Yet historical evidence suggests that Port Einon was commercially viable. This creates a technological puzzle. If operators relied entirely on direct boiling, fuel consumption would have been enormous. Experimental archaeology suggests that medieval salt production could require several tons of wood for every ton of finished salt. Such consumption would quickly exhaust local fuel supplies. So how did the Port Einon producers solve this problem? One theory proposes that they developed a multi-stage concentration process before boiling began. Instead of heating fresh seawater immediately, they may have first concentrated brine naturally through wind exposure and shallow holding ponds. By allowing Atlantic winds to remove part of the water content, the final boiling stage would require far less energy. The concept resembles techniques documented in French salt marshes and certain Roman salt works. However, no complete evidence for such a system has been found at Port Einon. Another possibility is even more intriguing. Researchers have suggested that local operators may have understood tidal concentration zones. Certain coastal pools can naturally accumulate higher salinity water due to repeated evaporation and tidal cycles. Harvesting water from these locations would dramatically improve production efficiency. If true, the workers possessed practical environmental knowledge that effectively functioned as a form of applied chemistry centuries before modern chemical science existed. Yet the greatest mystery remains the absence of technical documentation. No surviving manuals explain the process. No engineering plans describe the production system. The physical structure survives, but the knowledge behind it has largely disappeared. Salt is one of the most destructive substances for masonry. Modern engineers constantly battle salt crystallization, moisture penetration, and chemical degradation in coastal structures. Even reinforced concrete often suffers severe damage after decades of exposure to marine environments. Port Einon's Salt House faced a far harsher challenge. Its walls endured centuries of sea spray, Atlantic storms, humidity, and concentrated salt vapors generated during production. Yet significant portions of the structure remain standing. This raises questions about the materials used by its builders. Analysis suggests the mortar was likely produced using local limestone and shell-derived lime. However, researchers still debate why certain sections appear unusually resistant to marine deterioration. Some specialists have compared the phenomenon to the remarkable durability of Roman maritime concrete. While the materials are not identical, both cases suggest that historical builders may have understood local mineral properties far better than previously assumed. Were the builders intentionally selecting specific aggregates? Did repeated exposure to seawater alter the chemistry of the mortar in beneficial ways? The exact answer remains uncertain. Producing salt through boiling creates an enormous amount of steam. Without effective ventilation, working conditions become nearly impossible. High humidity reduces combustion efficiency, damages structures, and creates dangerous conditions for workers. Yet the surviving layout suggests that airflow may have been carefully controlled. Openings appear positioned to capture prevailing Atlantic winds. Some researchers believe the building may have functioned as a passive ventilation system using natural pressure differences to remove steam while maintaining efficient combustion. The concept resembles principles employed in modern industrial ventilation systems. If accurate, the builders achieved this without mathematical fluid dynamics models, computer simulations, or modern engineering tools. How they optimized airflow remains unknown. Perhaps the greatest logistical question concerns energy. Boiling tens of thousands of liters of seawater requires massive amounts of fuel. Historical estimates suggest that large-scale salt production operations could consume several tons of fuel each week. Where did Port Einon obtain enough energy to remain operational? The surrounding landscape could not indefinitely support unrestricted wood harvesting. Some historians believe fuel arrived by boat from other regions. Others suggest that coal may have been incorporated into the process earlier than historical records indicate. South Wales sits near some of Britain's richest coal deposits. If coal was being used systematically, it would significantly improve efficiency. Unfortunately, definitive evidence remains elusive. Salt was a valuable commercial commodity. It preserved food, supported fishing industries, and served numerous industrial purposes. For Port Einon to operate successfully, transportation infrastructure must have existed. Large quantities of salt could not simply be carried away by hand. Archaeologists suspect that docks, loading platforms, storage facilities, and maritime support structures once surrounded the site. Almost all of these features have vanished. Centuries of coastal erosion and Atlantic storms may have destroyed critical evidence. As a result, researchers are attempting to reconstruct an entire industrial network from only a handful of surviving clues. The location of the salt house itself may represent a sophisticated engineering decision. The structure occupies a position that balances access to seawater, protection from extreme wave action, and proximity to transportation routes. Modern coastal engineering relies heavily on hydrodynamic modeling and environmental analysis to make such decisions. The builders possessed none of these tools, yet their choice proved remarkably successful. The site survived for centuries in one of the most challenging coastal environments in Britain. Was this simply experience accumulated over generations? Or did medieval coastal engineers possess a practical understanding of environmental systems far more advanced than historians once believed? Perhaps the greatest mystery is not the building itself, but the loss of the knowledge that created it. The engineers behind Portaenon Salt House mastered fuel use, heat transfer, materials, and production organisation, turning seawater into a valuable commodity under difficult conditions. Yet little of their expertise survives. No detailed manuals, blueprints, or records explain how they optimized brine, designed furnaces, or improved efficiency. The stones remain, the evidence remains, but the methods are largely gone. What do you think? Were the engineers of Portaenon simply masters of practical experience, or did they possess production techniques that have been lost to history? Share your thoughts in the comments below. Denbigh, North Wales. For more than 400 years, a roofless church has stood exposed to rain, wind, frost, and time. Yet despite never being completed, many of its walls remain standing with remarkable stability. Even more intriguing, evidence suggests its designers may have been attempting something centuries ahead of their era, a building engineered around light itself. Construction began in 1578 under Robert Dudley, Earl of Leicester, one of Queen Elizabeth I's closest advisors. The church was intended to become one of the largest Protestant preaching churches in Britain. The project was abandoned before completion, leaving behind a giant stone shell that still dominates Denbigh today. The greatest mystery surrounding Leicester's church is not hidden underground. It is visible in every surviving wall. Most medieval churches were designed around ritual, with architecture that directed attention toward the altar and often created dim interiors illuminated by stained glass. Leicester's church appears to follow an entirely different philosophy. The surviving structure contains enormous Tudor-style window openings, positioned throughout the building, and even today, standing inside the ruins reveals an unusual amount of natural illumination compared with many medieval churches of similar size. Historians believe the building was designed as a Protestant preaching church rather than a traditional Catholic-style worship space. During the Reformation, spoken sermons became increasingly important, and large congregations needed to see and hear the preacher clearly. What remains unexplained is how the designers achieved such a sophisticated lighting strategy. No complete architectural plans survive. No engineering records explain the placement of the windows, and no calculations reveal how sunlight was expected to move through the interior throughout the year. Yet the arrangement appears intentional rather than decorative. Modern architectural researchers frequently use computer simulations to optimize daylight inside public buildings. Such analyses consider solar angles, seasonal changes, wall heights, and interior geometry. Leicester's designers possessed none of these tools. Nevertheless, the building demonstrates characteristics associated with deliberate daylight engineering. The main worship area was expected to receive significantly more natural illumination than many Gothic churches. The large window openings reduced interior shadows, and the design minimized visual barriers between preacher and congregation. The comparison is striking. While many medieval cathedrals created spiritual atmosphere through darkness and selective light, Leicester's church seems to have pursued visibility, openness, and brightness. How did 16th century builders achieve this without modern optics? Was the design based entirely on practical experience? Or had generations of master builders accumulated observational knowledge sophisticated enough to predict lighting performance with surprising accuracy? The answers remain unknown. Leicester's church measures approximately 55 meters in length and 23 meters in width. For its period, this was an ambitious project. Yet the most remarkable feature may be what never existed: the roof. The church was abandoned before completion, and for centuries the structure has stood without the protective element that most large masonry buildings require. From an engineering perspective, this creates an important puzzle. Roofs do more than keep rain out. They often help stabilize walls by distributing loads and tying structural elements together. When roofs disappear, masonry structures frequently become vulnerable to movement, cracking, and collapse. Examples can be seen throughout Europe, where numerous abandoned monasteries and churches suffered progressive deterioration after losing their roofs. Yet Leicester's church remains surprisingly intact. Many walls still stand close to their original height. Large window openings have survived, and the overall geometry of the structure remains recognizable. This suggests that the builders may have incorporated stronger wall systems and more robust foundations than originally required. Modern structural assessments indicate that wall thickness, stone quality, and construction methods likely contributed significantly to the building's survival. However, because construction records are incomplete, the full engineering logic behind the design remains uncertain. One of the most fascinating mysteries involves the interior. Historical sources indicate that the completed church would likely have contained Renaissance-inspired Tuscan columns supporting an extensive roof system. The problem is that nobody knows exactly what that roof would have looked like. No surviving plans describe the final arrangement. No drawings reveal the exact dimensions of the supporting columns, and no documents explain how loads would have been transferred across the enormous interior space. Archaeologists can identify foundations and construction traces, but these clues provide only fragments of the original design. Digital reconstruction projects have proposed several possibilities. Some models suggest a relatively simple timber roof, while others indicate a much more ambitious structure requiring advanced load distribution techniques. Without definitive evidence, the final engineering solution remains one of the church's greatest unanswered questions. Constructing a building of this scale required remarkable precision. The site occupies challenging terrain near the historic defences of Denby. Builders had to establish level foundations, maintain wall alignment, and preserve geometric accuracy across a structure more than 50 meters long. Today, engineers perform such tasks using laser scanners, GPS systems, digital modeling software, and electronic surveying instruments. The builders of Leicester's church had none of these technologies. Instead, they relied on ropes, plumb bobs, measuring rods, sighting methods, and practical geometry. Yet surviving walls demonstrate a degree of precision that continues to impress conservation specialists. This raises a larger historical question. How sophisticated were Renaissance surveying techniques compared with what modern observers typically assume? Many historical builders achieved extraordinary accuracy without mathematical tools recognizable today. Leicester's church may represent one of the clearest surviving examples of that forgotten expertise. North Wales presents a difficult environment for masonry structures. The region experiences frequent rainfall, strong winds, moisture penetration, and repeated freeze-thaw cycles. Over centuries, these forces can destroy even modern buildings, yet large sections of Leicester's church continue to survive. The durability of the stonework suggests careful material selection. Builders appear to have chosen stone capable of resisting weathering while maintaining structural integrity. The mortar presents an equally intriguing question. Many historical mortars possessed characteristics that modern researchers continue to study. Variations in lime composition, aggregate selection, curing techniques, and mixing methods could dramatically influence durability. Unfortunately, detailed construction records have disappeared. As a result, researchers can analyze surviving material samples, but cannot fully reconstruct the original manufacturing process. The historical explanation appears straightforward. Construction costs were enormous. Political priorities changed. Robert Dudley died in 1588 and funding disappeared. Yet the scale of the unfinished structure raises additional questions. The project had already consumed substantial resources. Large quantities of stone had been transported, extensive foundations had been completed, and walls had risen to impressive heights. Abandoning such an investment was not a trivial decision. Some historians point toward financial difficulties, while others emphasize political tensions, religious conflicts, or shifting priorities within Elizabethan England. The precise combination of factors remains debated. Ironically, the project's failure may have created its modern mystery. Had the church been completed, later renovations could have obscured evidence of its original engineering. Instead, the unfinished structure preserves clues frozen in time. Perhaps the greatest mystery is not the church itself, but the loss of the knowledge that created it. Its builders mastered masonry, surveying, structural design, and material selection, yet almost none of their technical records survive. This pattern is common in history. Like Roman aqueducts, Gothic cathedrals, and Inca fortresses, Leicester's church remains standing while much of the knowledge behind its construction has vanished. What do you think? Were the builders of Leicester's church simply masters of experience and observation, or did they possess engineering knowledge far more advanced than history has preserved? Share your thoughts in the comments below. Nestled in the remote Vale of Ues in the Black Mountains of southeastern Wales, the ruins of Llanthony Priory preserve one of medieval Europe's most overlooked engineering mysteries. Nearly 9 centuries after its construction, researchers still cannot fully explain how builders transported enormous quantities of stone into such an isolated valley, created structures capable of surviving extreme Welsh weather, and produced mortar whose long-term durability remains difficult to replicate today. The priory was founded around 1100 CE, near an earlier religious site associated with St. David. Archaeological investigations, architectural surveys, material analysis, and modern laser scanning over the last century have revealed a surprisingly sophisticated construction project hidden beneath the ruins. At first glance, Llanthony Priory appears to be another medieval monastic ruin, yet its location immediately raises questions. The priory sits deep within a narrow valley surrounded by steep mountains. Even modern visitors reach the site through winding roads that cut through difficult terrain. During the 12th century, there were no modern roads, no mechanized transportation, and no industrial lifting equipment. Yet builders somehow transported thousands of tons of sandstone and other construction materials into the valley. The nave alone once stretched approximately 60 meters in length, making it comparable in scale to major ecclesiastical structures elsewhere in Britain. The challenge becomes even more impressive when compared with other remote medieval sites. Tintern Abbey, for example, benefited from transportation along the River Wye. Many large Norman cathedrals were constructed near population centres or navigable waterways. Llanthony lacked both advantages. This raises an unresolved logistical question. How were massive quantities of building stone, timber, lime, tools, and food transported into such an isolated location year after year for decades? Historians can estimate the workforce required, but the precise logistical system remains largely undocumented. Before construction could begin, builders faced another challenge: understanding the landscape itself. Modern engineering projects rely on satellite mapping, laser surveying, geological analysis, and digital terrain models. 12th century builders possessed none of these technologies, yet the priory's layout demonstrates remarkable adaptation to local topography. The foundations were positioned to take advantage of stable ground, while minimizing the effects of seasonal runoff descending from the surrounding mountains. Recent surveys indicate that major structural alignments were carefully planned rather than improvised. Drainage paths, wall positions, and foundation levels suggest a sophisticated understanding of terrain behavior. The mystery is not that medieval builders were skilled. The mystery is how they achieved such precision without leaving behind detailed technical records explaining their methods. Across Europe, similar questions surround sites such as Machu Picchu, Mont Saint-Michel, and certain Cistercian abbeys. The structures survive, but the engineering knowledge often does not. Of all the technological puzzles at Llanthony Priory, perhaps none is more intriguing than the mortar itself. The Welsh climate is notoriously harsh on masonry. The region experiences high annual rainfall, persistent humidity, repeated freeze-thaw cycles, biological growth, and centuries of exposure to wind-driven moisture. Under such conditions, many modern cement repairs deteriorate surprisingly quickly. Yet portions of Llanthony's original masonry have survived for nearly 900 years. Scientific analysis has revealed that the mortar is not simply a crude mixture of lime and sand. Microscopic examination has identified complex mineral compositions, variable aggregate sizes, and evidence that builders deliberately adjusted mixtures according to construction needs. Researchers have discovered that many medieval mortars behaved differently from modern Portland cement. Rather than creating an extremely rigid structure, traditional lime mortars remained slightly flexible. This flexibility allowed walls to absorb minor movements caused by temperature changes, moisture fluctuations, and settlement without catastrophic cracking. Some studies of medieval mortars throughout Britain have also identified traces of organic additives, including animal-derived materials, plant products, and other substances that may have influenced curing behavior. The challenge is that no surviving document describes the exact recipe used at Llanthony. Questions remain regarding what type of limestone was selected, how long the lime was burned, what temperatures were achieved in medieval kilns, whether organic additives were intentionally introduced, and how mixtures were adjusted for different structural applications. Modern conservation specialists continue to study surviving mortar samples because understanding these ancient formulas could improve long-term restoration techniques. The mystery becomes even more fascinating when compared with Roman concrete. Roman harbour structures have survived for over 2,000 years, partly because of unique mineral reactions within their cement. Similarly, Llanthony's mortar may contain combinations of materials and construction practices that are not yet fully understood. In other words, the builders may have possessed practical materials science knowledge that was never formally recorded. Water was both a necessity and a threat. The valley surrounding Llanthony receives substantial rainfall. Seasonal streams, groundwater movement, and runoff from mountain slopes constantly interact with the site. Without proper drainage, foundations would gradually weaken, walls would shift, and structural deterioration would accelerate. Archaeological investigations have revealed evidence of sophisticated drainage systems integrated into the priory complex. Channels, culverts, and carefully managed water pathways appear to have directed moisture away from critical structures. What remains uncertain is the full scale of this network. Researchers continue to ask whether builders understood local groundwater patterns, whether drainage routes were planned before construction began, and how engineers predicted water behavior without modern hydrological modeling. Even today, drainage design remains one of the most critical aspects of construction in mountainous regions. The survival of substantial portions of Llanthony suggests that medieval builders solved problems that modern engineers still treat with great caution. The ruins visible today represent only a fraction of the original complex. Many roofs, vaults, upper walls, towers, and timber structures have disappeared, yet surviving architectural evidence indicates that these elements were once highly sophisticated. Stone vaulting in particular required extraordinary precision. Every block had to transfer loads through carefully calculated paths, and small errors could trigger progressive collapse. Builders possessed no structural analysis software, no computer simulations, and no modern understanding of material stress distribution. Yet medieval vaults throughout Europe routinely spanned impressive distances while supporting enormous weights. At Llanthony, surviving remains suggest that similar engineering principles were employed. The question remains, how much of this knowledge was based on mathematical understanding, and how much was accumulated through generations of experimentation? Another overlooked mystery involves sound. Religious architecture was designed not only to be seen, but also to be heard. The original church likely amplified chanting and liturgical music through carefully proportioned spaces. Large stone surfaces reflected sound, while vault geometry influenced resonance patterns. Modern acoustic engineers can model such effects using sophisticated software. Medieval builders could not. Yet many monastic and cathedral spaces across Europe demonstrate acoustic properties that appear remarkably effective. Was this simply trial and error accumulated over centuries? Or did builders possess empirical design principles that have never been fully documented? The answer remains uncertain. What do you think? Were the builders of Llanthony Priory simply masters of experience and observation? Or did they possess engineering knowledge that has largely been lost to history? Share your thoughts in the comments below. The eastern coast of Anglesey, Wales, overlooking the narrow waters of the Menai Strait, is home to the ruins of Castell Aberlleiniog, a site that conceals a mystery far greater than a medieval fortress. Beneath its earthworks lies evidence of engineering knowledge that historians still struggle to fully explain. Located near the town of Beaumaris on the Isle of Anglesey, Castell Aberlleiniog was first documented in medieval records dating to the Norman expansion into Wales during the late 11th and early 12th centuries. Archaeological excavations and modern LiDAR surveys have since revealed far more extensive defensive systems than previously believed. At first glance, Castell Aberlleiniog appears to violate one of the most basic principles of medieval military architecture. Most Norman castles were constructed on high ground because elevation provided superior visibility, greater defensive advantages, and natural protection against attack. Famous examples such as Dover Castle, Bamborough Castle, and numerous Welsh fortresses all exploited elevated terrain. Yet Castell Aberlleiniog sits relatively close to sea level near coastal wetlands. Why would experienced Norman military engineers choose such a location? The answer remains unclear. Modern terrain analysis suggests the builders may have prioritized control of transportation routes rather than purely defensive advantages. The castle occupies a strategic position overlooking approaches between Anglesey and mainland Wales through the Menai Strait, one of the most important waterways in the region. Computer-based visibility studies indicate that observers stationed within the fortress could monitor both maritime and inland movement across a surprisingly large area. In effect, the location functioned less like an isolated stronghold and more like a surveillance platform controlling regional movement. What remains unexplained is how Norman engineers identified this optimal location without modern mapping technology, aerial surveys, satellite imagery, or advanced geographic measurements. Their decision appears remarkably sophisticated even by modern military planning standards. The most impressive surviving feature of Castell Aberlleiniog is not a tower or stone wall, it is the earth itself. Large defensive ditches and embankments still surround the site, and archaeologists estimate that thousands of cubic meters of soil were excavated and relocated during construction. For a relatively modest fortress, the scale of the earthworks appears unusually large. This raises a significant question. Why invest such extraordinary labour into moving vast quantities of earth when many Norman castles relied primarily on timber fortifications? Recent studies of medieval fortifications suggest that earthworks provided advantages often underestimated by modern observers. Massive embankments absorbed impacts more effectively than stone walls against certain siege technologies, while deep ditches forced attackers into predictable paths, creating deadly defensive kill zones. Computer simulations performed on similar Norman fortifications demonstrate that carefully designed earthworks could increase defensive efficiency dramatically, allowing smaller garrisons to resist larger attacking forces. Yet no surviving engineering documents explain how medieval builders calculated ditch depths, embankment angles, or defensive geometries. The earthworks of Castel Aberlleiniog may preserve practical military mathematics that disappeared centuries ago. Water has always been one of the most important elements in military engineering. A fortress with too much water becomes unstable, while a fortress with too little loses valuable defensive advantages. Castel Aberlleiniog presents a fascinating puzzle because it was constructed near wetlands, coastal zones, and fluctuating groundwater conditions. Excavations have identified possible drainage channels beneath portions of the defensive earthworks, suggesting deliberate attempts to manage water movement throughout the site. The sophistication of the system remains debated. Some researchers believe the builders possessed an advanced practical understanding of local hydrology, developed through generations of observation, while others argue that the drainage network may represent later modifications. What makes the mystery particularly intriguing is that similar hydraulic solutions appear in medieval castles hundreds of kilometres apart. Sites such as Caerphilly Castle and several Norman fortifications in England demonstrate surprisingly effective water management systems despite being constructed long before the development of modern engineering science. The question remains unanswered: how did medieval builders consistently manipulate groundwater and surface water without geological surveys, computer modelling, or modern hydraulic calculations? Of all the engineering puzzles surrounding Castel Aberlleiniog, none may be more fascinating than its foundations. This mystery lies beneath the visible ruins. The castle was not constructed on solid mountain bedrock. Instead, significant portions of the site occupy relatively soft coastal ground, influenced by moisture, sediment movement, and long-term environmental change. From an engineering perspective, this should have been a major problem. Modern construction on weak soil often requires deep foundations, reinforced concrete piles, geotechnical analysis, and extensive drainage systems. Without such measures, structures can sink, tilt, crack, or collapse. Yet Castel Aberlleiniog survived for centuries. Archaeological investigations suggest that the builders may have employed layered foundation systems composed of compacted earth, gravel, stone fragments, and carefully selected fill materials. This approach bears remarkable similarities to principles used in modern geotechnical engineering. Today, engineers improve weak ground by distributing loads across wider surfaces, increasing drainage capacity, reducing water retention, and minimizing uneven settlement. Evidence from Castel Aberlleiniog suggests medieval builders may have achieved comparable results using entirely empirical methods. The challenge is that no construction manuals survive. No drawings explain how the ground was prepared. No records describe how materials were selected, and no documents reveal how settlement was monitored. What astonishes modern researchers is that many foundation failures in contemporary construction occurred despite sophisticated engineering software. Yet, medieval builders working without mathematics as we know it managed to create structures that remained stable for generations. This mystery is not unique to Castel Aberlleiniog. Similar questions surround the foundations of Venice, where millions of wooden piles support entire districts. They also appear at Mont Saint-Michel in France and numerous medieval waterfront fortifications throughout Europe. In every case, builders demonstrated an ability to understand soil behavior long before geotechnical engineering existed as a scientific discipline. The fortress may therefore preserve evidence of a forgotten engineering tradition based entirely on observation, experimentation, and accumulated practical knowledge. The castle's position offers visibility toward multiple strategic locations around the Menai Strait. This has led some historians to propose that Castel Aberlleiniog may have been part of a larger signalling network. Throughout medieval Europe, warning systems frequently relied on fire beacons, smoke signals, and visual communication stations positioned across long distances. Under favourable conditions, such systems could transmit warnings dramatically faster than horseback messengers. The problem is that physical evidence rarely survives. Wooden beacon towers disappear, signal platforms erode, and documents are lost. As a result, researchers can only reconstruct fragments of these communication systems. If Castel Aberlleiniog participated in such a network, it may have functioned as an important information hub, controlling maritime traffic and military intelligence across northern Wales. The technological organisation required for such a system remains poorly understood. One reason Castel Aberlleiniog remains mysterious is that much of the original fortress was built from timber rather than stone. Wood rarely survives for centuries in exposed environments. As a result, the visible ruins represent only a fraction of the original complex. Excavations have revealed post holes indicating substantial wooden buildings, towers, defensive walls, and internal structures. These discoveries suggest a much larger and more sophisticated fortress than earlier historians imagined. Yet reconstruction remains difficult. Researchers know where some structures stood, but they cannot fully determine their height, load-bearing systems, construction methods, or architectural details. The result is a castle that remains partially invisible. Its surviving earthworks preserve the footprint of lost engineering, while the structures themselves have disappeared almost entirely. What do you think? Were the engineers of Castel Aberlleiniog simply masters of experience and observation? Or did they possess technical knowledge far more advanced than history has given them credit for? Let us know your thoughts in the comments below. Greenfield Valley, Flintshire, North Wales, is a narrow valley crossed by streams, abandoned mills, and forgotten stone channels. At first glance, it looks like a quiet industrial heritage site. Yet hidden beneath the landscape lies evidence of hydraulic engineering, so precise that some of its methods remain difficult to fully explain today. The valley's historical significance emerged through archaeological investigations, industrial surveys, and restoration projects conducted throughout the 20th century. Researchers uncovered extensive networks of water channels, mill foundations, underground conduits, and mechanical systems that revealed centuries of continuous engineering development. Long before modern power stations existed, water was the primary source of industrial energy. Across Greenfield Valley, generations of builders transformed a natural stream system into a vast hydraulic machine capable of powering mills, workshops, factories, and processing facilities. What makes this remarkable is the level of control they achieved. The valley contains evidence of artificial channels, diversion systems, storage ponds, overflow controls, and water management structures spread across multiple elevations. These systems allowed engineers to regulate water flow with surprising precision. Modern hydraulic engineers understand that even minor errors in gradient can cause serious problems. A channel that is too steep accelerates erosion, while a channel that is too shallow reduces flow velocity and power output. Yet many surviving channels maintain gradients that remain functional centuries after construction. Researchers studying historic water management systems have repeatedly noted that medieval and early industrial builders often achieved remarkable accuracy without modern surveying equipment. Similar examples can be found in Roman aqueducts, which sometimes maintained gradients of only a few centimeters per kilometer. Greenfield Valley appears to belong to that same tradition of practical engineering knowledge. The question is simple. How did builders achieve such precision without lasers, satellites, electronic measuring devices, or modern engineering mathematics? No complete technical manuals survive to provide the answer. Water is both a source of power and an enemy of construction. Much of Greenfield Valley consists of ground exposed to constant moisture, seasonal flooding, and unstable soil conditions. Modern engineers would normally conduct extensive geological surveys before placing heavy structures in such an environment. Yet many historic foundations survived for centuries, and large mills, processing buildings, and industrial facilities operated continuously despite challenging ground conditions. Archaeological investigations have revealed sophisticated foundation techniques involving stone platforms, drainage systems, load distribution strategies, and carefully selected building locations. What remains unclear is how engineers identified stable ground so accurately. There were no geological maps, no drilling rigs, and no computer simulations. Nevertheless, builders repeatedly selected locations capable of supporting massive structures while avoiding many of the unstable areas surrounding them. This pattern is not unique to Greenfield Valley. Similar questions surround medieval cathedrals, Inca mountain fortresses, and numerous ancient engineering projects worldwide. The structures survive, but the calculations behind them often do not. Perhaps the most fascinating engineering puzzle in Greenfield Valley involves the giant water wheels that once powered the valley's industries. Today, water wheels are often viewed as simple machines. In reality, large industrial water wheels were among the most sophisticated mechanical systems of their era. Some 19th century water wheels in Britain exceeded 10 meters in diameter and generated power comparable to dozens of human laborers working simultaneously. A properly designed overshot wheel could achieve efficiencies approaching 70 to 85% under ideal conditions. Remarkably, this is comparable to the efficiency range of many early steam engines. Such performance required extraordinary engineering precision. Every variable mattered, including wheel diameter, bucket geometry, flow rate, water volume, rotational speed, weight distribution, axle alignment, and material strength. Even slight design errors could dramatically reduce performance. Archaeological evidence from Greenfield Valley suggests that engineers developed highly optimized wheel systems capable of powering multiple industrial operations simultaneously. The mystery lies in how they acquired this knowledge. No surviving engineering documents fully explain the design process. No detailed construction blueprints reveal how wheel dimensions were calculated. No records describe how engineers determined the optimal relationship between water volume and rotational speed. Modern reconstructions indicate that successful wheel operation required balancing dozens of interconnected variables. Yet historical builders achieved these results repeatedly. The challenge becomes even greater when considering maintenance. A large water wheel could contain thousands of individual wooden and metal components. Continuous exposure to moisture, changing temperatures, and heavy loads created constant stress on the structure. Despite these challenges, some wheels operated reliably for decades. Experimental archaeologists attempting to recreate historical wheel systems have discovered that apparently simple designs often conceal extremely sophisticated engineering principles. Fluid dynamics, momentum transfer, structural mechanics, and energy optimization all played critical roles. Many of these principles were understood through experience rather than formal scientific theory. The builders knew what worked, but what remains uncertain is how they learned it. Beneath the visible landscape lies another mystery. Archaeological surveys have identified sections of underground channels, drainage tunnels, culverts, and concealed water management systems running beneath parts of the valley. Some were designed to prevent flooding, others redirected water toward industrial facilities, and some may have served multiple purposes simultaneously. Many of these structures remain only partially understood. Several were modified repeatedly over centuries, making it difficult to determine their original design. What impresses engineers today is their effectiveness. Even after decades or centuries of use, many systems continue to manage water flow successfully. This raises important questions. How are these tunnels surveyed underground? How are gradients maintained without modern instruments? How are structural failures prevented? The answers remain incomplete. Near the valley stand the remains of Basingwerk Abbey, a Cistercian monastery founded during the 12th century. The Cistercians were among the most technologically advanced monastic orders in medieval Europe. Across the continent, they became famous for their expertise in water management, milling technology, metallurgy, and agricultural engineering. Many historians suspect that at least part of Greenfield Valley's hydraulic tradition may trace its origins to knowledge developed or preserved by these monks. The problem is evidence. Large portions of medieval documentation have disappeared, construction records are incomplete, and technical instructions rarely survived. As a result, historians cannot fully reconstruct how knowledge moved from monastic communities into later industrial systems. This creates a fascinating possibility. Some engineering techniques used in the valley may represent centuries of accumulated expertise, whose origins have been largely forgotten. Another mystery concerns resource extraction. For centuries, local industries exploited stone, clay, minerals, and other natural resources found throughout the region. Many extraction sites were located in geologically favorable areas. Today, identifying such locations often requires detailed surveys, geological mapping, laboratory analysis, and remote sensing technologies. Historical workers had none of these tools, yet they repeatedly discovered productive deposits. Researchers suspect that generations of observation allowed workers to recognize subtle environmental clues invisible to most people. These clues may have included variations in vegetation, changes in soil coloration, water chemistry, rock exposures, and drainage patterns. Individually, these indicators may seem insignificant. Together, they may have formed a practical geological science developed through centuries of experience. The full extent of that knowledge remains unknown. What do you think? Were the engineers of Greenfield Valley simply masters of observation and experience, or did they possess practical engineering knowledge far more advanced than history has given them credit for? Let us know your thoughts in the comments below. Llantysilio Valley, North Wales. For more than 800 years, the ruins of Valle Crucis Abbey have stood on land that should never have supported a structure of this size. Built beside a river, surrounded by waterlogged ground and exposed to centuries of rain, flooding, and erosion, the monastery still preserves evidence of engineering that modern researchers struggle to fully explain. Founded in 1201 by Madog ap Gruffydd Maelor, Prince of Powys-Fadog, Valle Crucis Abbey belonged to the Cistercian order. Archaeological investigations, restoration projects, geological surveys, and modern laser mapping have revealed that beneath its ruined walls lies a sophisticated system of foundations, drainage, and construction techniques that continue to raise difficult questions about medieval engineering. Perhaps the greatest mystery of Valle Crucis Abbey lies beneath the visible ruins. The abbey was constructed on the floor of the Dee Valley, an area known for high groundwater levels, seasonal flooding, and soft alluvial deposits. Modern civil engineers generally avoid placing massive stone buildings on such terrain without extensive foundation preparation because waterlogged soils often compress unevenly under heavy loads, producing cracks, tilting walls, and eventual structural failure. Yet Valle Crucis survived for centuries. The church alone measured approximately 68 meters in length, requiring thousands of tons of stone. Combined with the cloisters, chapter house, dormitories, workshops, and supporting structures, the total weight imposed on the ground would have been enormous. The problem becomes even more intriguing when compared with other medieval sites. Many castles built on rocky hills, such as Caernarfon Castle and Conwy Castle, benefited from naturally stable foundations, while Valle Crucis had no such advantage. Archaeologists have identified evidence suggesting that the builders carefully selected slightly elevated sections of ground and may have modified the natural landscape before construction began. However, no detailed records survive explaining how these decisions were made. This raises an extraordinary question. How did medieval builders determine subsurface stability without geological surveys, borehole testing, soil analysis laboratories, or computer simulations? Even today, foundation investigations often require drilling equipment, seismic testing, and groundwater measurements. The Cistercian builders possessed none of these technologies. Some researchers suggest that generations of accumulated practical knowledge allowed medieval builders to recognize subtle environmental indicators. Vegetation patterns, soil color, drainage behavior, seasonal moisture changes, and animal activity may have revealed hidden geological conditions. But practical observation alone may not fully explain the results. Recent structural assessments indicate that settlement across surviving sections of the abbey remains remarkably limited considering the site's age and environmental conditions. In some locations, deformation appears significantly lower than engineers might expect after 8 centuries of exposure. The exact methods used to achieve such stability remain unknown, and the foundations continue to represent one of the most compelling unsolved engineering mysteries at Valle Crucis. Closely connected to the foundation mystery is another remarkable achievement: water management. These Cistercians were famous throughout medieval Europe for hydraulic engineering, and Valle Crucis appears to have been one of their most sophisticated examples. Excavations have revealed channels, drains, culverts, and water control features integrated throughout the monastery complex. These systems performed several functions simultaneously, moving wastewater, reducing groundwater accumulation, protecting foundations from saturation, and controlling runoff during periods of heavy rainfall. What makes this particularly impressive is the precision required. Modern drainage engineers understand that even minor errors in gradient can dramatically reduce effectiveness. A slope that is too steep causes erosion, while one that is too shallow allows water to stagnate. Yet many surviving drainage elements continue to demonstrate effective water movement centuries after construction. This raises another question. How are such gradients measured? The builders possessed no laser levels, no digital surveying instruments, and no satellite positioning systems. Nevertheless, the hydraulic network functioned with remarkable efficiency, and the methods used to design and implement this system remain only partially understood. The visible ruins reveal another mystery: accuracy. Large sandstone blocks were extracted, transported, shaped, and assembled with exceptional precision. Many joints remain surprisingly tight despite centuries of weathering. Creating such masonry required mastery of geometry, measurement, and craftsmanship. Each stone had to fit within a larger structural system while supporting enormous loads. The challenge becomes even greater when considering transportation. Some stones likely weighed hundreds of kilograms, and moving them across medieval roads, muddy terrain, and uneven landscapes would have required careful planning and sophisticated logistics. No complete construction plans survive, and no technical manuals explain the procedures. The builders clearly possessed advanced practical knowledge, but much of that knowledge disappeared long ago. Today, the sky fills spaces once covered by timber and stone. The original roofing system has largely vanished, yet surviving architectural evidence suggests that the abbey once possessed a highly sophisticated structure capable of withstanding Wales's demanding climate. North Wales experiences heavy rainfall, strong winds, and frequent seasonal storms. Any roof covering a building of this scale would have faced enormous environmental stress. Computer reconstructions indicate that the roof likely distributed loads through an intricate combination of timber framing and stone supports. However, researchers still debate critical details of the design. Without surviving engineering drawings, many aspects remain hypothetical. Even modern digital modelling cannot fully reconstruct every component with certainty. The exact solutions employed by medieval builders remain elusive. The abbey was designed for worship, and everyday monks gathered to chant prayers and hymns. Modern acoustic studies of Gothic and Cistercian architecture have demonstrated that building geometry can dramatically influence sound propagation. At Valle Crucis, surviving architectural proportions suggest that sound may have been amplified and distributed throughout the church with remarkable effectiveness. Was this intentional, or was it an accidental consequence of Gothic design principles? The answer remains uncertain. If intentional, the builders were manipulating acoustic physics centuries before formal scientific descriptions of resonance and wave behavior existed. Constructing Valle Crucis required extraordinary organization. Thousands of tons of stone had to be quarried, timber had to be harvested and transported, lime had to be produced for mortar, and food had to be supplied to workers. Construction likely continued for decades. Modern project managers rely on schedules, engineering software, transportation networks, and extensive documentation. The medieval builders relied on none of these tools, yet the abbey emerged as one of the most important monastic complexes in Wales. How labour, resources and transportation were coordinated so effectively remains a subject of ongoing investigation. What do you think? Were the builders of Valle Crucis Abbey relying solely on centuries of practical experience? Or did they possess engineering knowledge that has been lost to history? Share your thoughts in the comments below. Tamil Nadu, southern India. Across remote cave walls, weathered rock shelters, and fragments of ancient pottery, a script over 2,000 years old continues to challenge archaeologists. Known as Tamil Brahmi, these inscriptions preserve one of the earliest written traditions in South Asia. Yet the deeper researchers investigate, the more they encounter a remarkable mystery. The writing survives, but much of the technology, knowledge, and infrastructure that created it has disappeared. The first Tamil Brahmi inscriptions were identified during the 19th and early 20th centuries by epigraphists studying cave inscriptions across Tamil Nadu. Later excavations at sites such as Mangulam, Jambai, Kodumanal, Porunthal, Adichanallur, and Kieladi uncovered additional inscriptions on stone, pottery, and trade goods, revealing a surprisingly widespread writing system, dating roughly between the 3rd century BCE and 3rd century CE. One of the greatest debates surrounding Tamil Brahmi concerns its origin. Conventional scholarship links it to the Brahmi script that spread across the Indian subcontinent during the Mauryan Empire under Ashoka in the 3rd century BCE. According to this view, Tamil-speaking communities adapted Brahmi to represent sounds unique to the Tamil language. However, recent archaeological discoveries have complicated this picture. Excavations at Porunthal and Kieladi have produced pottery fragments bearing Tamil Brahmi inscriptions that some researchers argue may date earlier than expected. Radiocarbon analysis from associated layers has suggested dates extending into the 6th century BCE in certain cases, though interpretations remain debated. If these dates are correct, the implications are enormous. Rather than simply borrowing a northern script, ancient Tamil societies may have been developing literacy much earlier than previously believed. Yet no transitional form has been discovered. Archaeologists have not found the missing developmental stages that would explain how the script emerged, evolved, and became standardized. This mirrors mysteries seen elsewhere in history. Egyptian hieroglyphs appear already highly developed in their earliest forms. Sumerian cuneiform emerges rapidly from administrative markings into a sophisticated writing system. Tamil Brahmi presents a similar puzzle. A mature script appears in the archaeological record with much of its earlier evolution seemingly absent. Many Tamil Brahmi inscriptions were carved into granite cave surfaces. This may sound straightforward until one considers the material involved. Granite ranks between 6 and 7 on the Mohs hardness scale, and remains one of the most difficult natural stones to carve accurately. Yet many inscriptions display remarkable consistency. Individual characters maintain proportional dimensions. Lines often follow precise horizontal alignments across uneven rock surfaces, and depth variations remain surprisingly small despite the challenges of working on natural stone. The craftsmen responsible had no laser levels, no steel rulers, and no modern surveying equipment. This raises important questions about how these inscriptions were planned, how character proportions were maintained across large surfaces, and how craftsmen avoided cumulative errors while carving directly into rock. Modern three-dimensional scans of ancient inscriptions have revealed that many characters were executed with impressive geometric consistency. Experimental archaeologists attempting to replicate similar inscriptions using reconstructed Iron Age tools frequently discover that achieving such precision requires extensive training and careful planning. The inscriptions therefore represent not only language but also evidence of highly developed technical craftsmanship. Perhaps the most overlooked mystery concerns consistency. Tamil Brahmi inscriptions have been discovered across hundreds of kilometers of southern India and Sri Lanka, and sites separated by vast distances often employ remarkably similar character forms. In the modern world, standardization is easy because printed books, digital communication, schools, and official institutions ensure that written symbols remain consistent. Ancient Tamil society possessed none of these advantages, yet the script maintained recognizable forms across large geographic regions. This raises difficult questions. Did specialized schools train scribes? Were there official models for character formation? Did trade networks distribute writing standards? Or did a class of professional record keepers travel between settlements, maintaining literacy traditions? Archaeological evidence provides few answers. The consistency itself demonstrates the existence of organizational systems that remain largely invisible today. Tamil Brahmi inscriptions are not confined to inland settlements. Evidence suggests connections between Tamil-speaking merchants and trade routes extending across the Indian Ocean. Artifacts linked to South Indian commerce have been identified in Sri Lanka, the Arabian Peninsula, Egypt, and Southeast Asia. Ancient Tamil ports participated in one of the largest commercial systems of the ancient world. Roman records describe ships carrying pepper, pearls, gemstones, ivory, textiles, and exotic goods from South India, while the Periplus of the Erythraean Sea, written during the 1st century CE, documents maritime trade stretching thousands of kilometers. Such trade required record keeping. Cargoes had to be identified, ownership had to be tracked, and commercial agreements had to be preserved. Tamil Brahmi inscriptions found on pottery may represent part of this administrative infrastructure, yet almost none of the supporting documents survive. The trade system is visible, but the paperwork has vanished. For many years, historians assumed literacy was restricted to elites. However, discoveries from sites such as Kodumanal and Keladi have challenged that assumption. Researchers have uncovered numerous pottery fragments bearing personal names, symbols, and short inscriptions. Some appear to have been scratched by ordinary users rather than professional stone carvers. If this interpretation is correct, literacy may have been more widespread than previously believed. This creates a major historical puzzle. A population with significant literacy requires education. Education requires teachers. Teachers require institutions, and institutions leave traces. Yet evidence for large-scale educational systems remains surprisingly limited. The inscriptions hint at a literate society that archaeology has only partially revealed. Perhaps the most fascinating mystery of all involves something that no longer exists. The inscriptions carved into stone are almost certainly only a tiny fraction of what ancient Tamil society actually wrote. No civilization records its daily business primarily on granite cliffs. Letters, contracts, trade records, religious texts, inventories, poetry, administrative reports, tax records, and commercial agreements would have required portable writing materials, yet almost none survive. The climate of southern India provides part of the answer. High humidity, monsoon rains, heat, insects, fungi, and microbial activity destroy organic materials with extraordinary efficiency. Researchers believe that ancient Tamil scribes probably wrote on palm leaves, wooden tablets, bark, cloth, or other biodegradable surfaces. The problem is that these materials disappeared long ago. This creates an archaeological paradox. We possess evidence that a writing culture existed, evidence that literacy was widespread, and evidence that trade required record keeping. Yet the actual tools responsible for most writing have vanished. No verified collection of early Tamil Brahmi pens survives. No ink recipes have been preserved from the earliest period. No complete writing kits have been recovered. No administrative archives comparable to those of Egypt or Mesopotamia have been found. Imagine trying to understand the modern world if every book, computer, phone, notebook, and hard drive disappeared, leaving only a few engraved monuments behind. That is essentially the situation researchers face with Tamil Brahmi. The surviving inscriptions may represent less than 1% of the original written output of the civilization, while the other 99% may have vanished forever. This mystery extends beyond simple preservation. Without the original writing tools, scholars cannot fully reconstruct how texts were copied, how knowledge was transmitted, how education functioned, or how information moved across the ancient Tamil world. The script survives, but the technology of writing largely does not. What do you think? Does Tamil Brahmi represent the visible remains of a far larger literacy system that has vanished? Or have archaeologists only uncovered a small fraction of an even older and more sophisticated tradition? Let us know your thoughts in the comments below. Dolphin Castle, located near Montgomery in Powys, Wales, was identified through 19th century antiquarian surveys before large-scale archaeological investigations revealed the remains of one of medieval Wales' most ambitious native fortresses. Built around AD 1273 by Llywelyn ap Gruffydd, the last independent Prince of Wales, the castle stands on a prominent ridge overlooking the Severn Valley. At first glance, Dolphin appears to be just another ruined medieval stronghold. However, beneath its weathered stone walls lies a series of engineering mysteries that continue to challenge archaeologists, military historians, and construction experts. More than 7 centuries after its fall, the castle still raises important questions about surveying methods, logistics, defensive architecture, hydrological engineering, and the disappearance of the technical knowledge that once enabled builders to construct powerful fortifications in some of the most challenging landscapes in Britain. The first mystery begins with the selection of the castle's location. Modern topographical analysis shows that Dolphin occupies an exceptionally advantageous position. The ridge provides extensive visibility over strategic routes connecting central Wales with the English borderlands. Military studies suggest that observation from elevated defensive positions can extend early warning capabilities by several kilometers, giving defenders valuable time to prepare for approaching forces. What puzzles researchers is how 13th century builders identified such an optimal site without modern surveying equipment. The ridge itself is narrow, uneven, and surrounded by steep slopes. Yet the castle was positioned almost exactly where the natural terrain offered the greatest defensive advantage. Similar questions arise regarding Machu Picchu in Peru and the hilltop fortresses of the Inca Empire. In each case, ancient builders selected locations that modern geographical analysis confirms were remarkably effective. The methods used to identify these sites remain largely undocumented. Archaeological investigations reveal that Dolfewin's design differed significantly from many contemporary Norman castles. Rather than imposing a symmetrical layout on the landscape, the builders adapted every section of the fortress to the natural contours of the hill. The curtain walls curve, vary in thickness, and follow irregular lines. For centuries, historians assumed this asymmetry reflected limited engineering capability. Recent analyses, however, suggest the opposite. Computer simulations of attack scenarios indicate that irregular wall geometry often created overlapping fields of fire, improving defensive effectiveness. Certain sections of the walls were deliberately reinforced, while others relied more heavily on natural slopes. Modern military engineers refer to this concept as terrain integration, a strategy in which natural geography becomes an integral part of the defensive system. The mystery lies in whether medieval Welsh builders developed these solutions through trial and error, or possessed a more sophisticated understanding of a defensive geometry than surviving records suggest. The transportation of construction materials presents another unresolved question. Estimates suggest that thousands of tons of stone were used to build Dolfewin Castle. Much of this material had to be quarried, shaped, transported, and lifted to the top of a steep hill. Experimental archaeology projects have demonstrated that moving large stone blocks without mechanized equipment requires enormous manpower and careful coordination. A single block, weighing several hundred kilograms, may require dozens of workers using ropes, sledges, rollers, and temporary ramps. Yet no surviving documents describe how the builders organized this effort. Similar logistical mysteries appear throughout history. The construction of the pyramids involved moving approximately 6 million tons of stone. The builders of Sacsayhuaman transported blocks weighing more than 100 tons. Although Dolfewin was smaller in scale, the fundamental question remains the same. How were labor forces coordinated, supply chains maintained, and construction schedules managed without detailed technical documentation? Equally fascinating is the durability of the surviving stone walls. Wales experiences substantial rainfall throughout the year. In many regions, annual precipitation exceeds 1,000 millimeters. Such conditions typically accelerate erosion, weaken mortar, and increase damage caused by freeze-thaw cycles. Nevertheless, much of Dolfewin's masonry remains standing after more than 700 years. Material analyses indicate that medieval lime mortar was used throughout the structure. Even so, researchers continue to debate whether local craftsmen employed specialized mixtures optimized for the Welsh climate. Comparable studies of Roman concrete have revealed chemical processes that allowed structures to survive for millennia. Research published in recent years has shown that Roman marine concrete can actually become stronger through interaction with seawater. Did medieval Welsh masons possess practical knowledge of mortar formulations that has since been lost? Although there is no evidence of any extraordinary lost material, the precise techniques used to maximize durability remain poorly understood. One of the most intriguing mysteries concerns water management. A fortress can survive a siege only if it maintains a reliable water supply. Historical records show that medieval sieges sometimes lasted for months or even years. The famous siege of Kenilworth in England, for example, lasted approximately 6 months during the 13th century. Dolfewin was built on a ridge without an obvious natural spring capable of supplying a large garrison. Archaeologists have identified cisterns, drainage channels, and collection systems that were likely used to capture and store rainwater. The question is whether the surviving remains represent the entire system. Hydrological studies indicate that even relatively small catchment areas can collect significant amounts of water in regions with high annual rainfall. Some researchers believe that the original water management network may have been far more sophisticated than current evidence suggests. If true, Dolphin would represent an impressive example of medieval environmental engineering. Another mystery involves structural stability. Castle walls are not merely vertical barriers, they must withstand their own weight, environmental stresses, ground movement, and potential attacks. Modern structural engineering relies on mathematical calculations to estimate loads and stresses. Medieval builders did not possess formal engineering equations in the modern sense, yet their structures often demonstrate remarkable stability. At Dolphin, the foundations were adapted to uneven bedrock and varying soil conditions. The builders appear to have understood where additional reinforcement was necessary and where natural rock formations could safely bear structural loads. This practical knowledge resembles what has been observed at many other historic sites, including Europe's great cathedrals and the fortifications of the Crusader states. These structures survived because their creators understood structural behavior, even if they expressed that knowledge through experience rather than mathematics. The military effectiveness of Dolphin presents another puzzle. In 1277, King Edward IV of England captured the castle during his campaign against Welsh independence. Yet modern analysis suggests that the fortress was far from weak. Defensive studies indicate that attackers advancing uphill would have been exposed to missile fire for extended periods. The narrow ridge restricted troop movement and prevented large assault formations from advancing efficiently. Archaeologists have identified features suggesting deliberate planning aimed at maximizing defensive advantages. Had circumstances been slightly different, the fortress might have resisted for much longer. This raises an intriguing possibility. Was Dolphin merely a regional stronghold, or was it an experimental expression of an evolving Welsh military architecture? The final and perhaps greatest mystery is the loss of the knowledge itself. Dolphin's builders clearly possessed advanced skills in surveying, construction, and military design developed over generations. Yet little of this expertise survives. No manuals, engineering texts, or records explain how they measured, built, organized labor, or managed construction. Perched high above the town of Llangollen in northern Wales, Castell Dinas Bran is one of Britain's most enigmatic hilltop fortresses. Rising approximately 321 metres above sea level, the ruins visible today were constructed during the 13th century by the Welsh prince Gruffydd Maelor II. Archaeologists first began systematic investigations during the 19th century, yet nearly 2 centuries of research have failed to answer some of the site's most intriguing questions. Beneath the ruined walls lies evidence of engineering, surveying, logistics, and landscape management that remains only partially understood. What appears at first glance to be a simple medieval castle may in fact preserve traces of much older traditions and technological knowledge whose details have largely vanished. The first mystery concerns the hill itself. Dinas Bran occupies what many military historians consider an almost perfect defensive position. Modern topographic analysis shows that the summit commands views across the Dee Valley for many kilometers in multiple directions. Any movement through the valley would have been visible long before attackers approached the fortress. What makes this remarkable is the precision with which the location was selected. Medieval builders possessed no satellite imagery, aerial photography, GPS systems, or modern geographic and information software. Yet they chose a summit that maximized visibility while minimizing vulnerabilities. Similar strategic placement can be observed at sites such as Maiden Castle and Dunnottar Castle, but Dinas Bran achieves this advantage on an exceptionally isolated peak. Researchers still debate whether this positioning resulted from generations of accumulated local knowledge or from surveying techniques more sophisticated than surviving records suggest. An even greater mystery involves construction logistics. The castle stands atop a steep limestone hill where gradients in some areas exceed 30 degrees. Every block of stone, every timber beam, every tool, and every supply item had to be transported hundreds of meters uphill. Modern estimates suggest that several thousand tons of building material were required during construction. Without motorized transport, cranes, or modern lifting equipment, the builders somehow moved these materials to one of the most inaccessible construction sites in medieval Wales. Archaeologists have proposed ramps, sledges, wooden rollers, animal traction, and pulley systems. Yet no definitive evidence survives to confirm which method was actually employed. Similar questions surround the transport of stone at sites such as Machu Picchu and Sacsayhuaman, where enormous logistical achievements remain difficult to reconstruct. Dinas Bran may not involve stones weighing hundreds of tons, but the challenge of moving thousands of smaller blocks to such an extreme elevation remains impressive even by modern standards. The geology of the site introduces another puzzle. The castle sits upon limestone formations that have remained remarkably stable despite centuries of exposure to wind, rain, frost, and erosion. Modern geotechnical engineers carefully evaluate load-bearing capacity before constructing on elevated terrain, yet medieval builders possessed no formal geological science. Somehow they selected foundation points capable of supporting substantial defensive structures for centuries. The surviving ruins demonstrate that the builders understood which areas of bedrock could safely support walls and towers. Whether this knowledge came from observation, empirical testing, inherited traditions, or some combination of all three remains unknown. Similar mysteries exist at sites like Meteora, where builders established structures atop seemingly impossible rock formations long before modern engineering principles were formalized. One of the most debated questions concerns what existed before the medieval castle. Archaeological evidence suggests that the hill may have been occupied during the Iron Age, potentially more than 2,000 years before the castle was built. Earthworks and defensive features hint at an earlier hill fort, although much of the evidence has been disturbed by later construction. If an Iron Age fortress once occupied the summit, its builders would have faced many of the same engineering challenges encountered by medieval builders. They would have needed to stabilize slopes, organize labor, transport materials, and establish defensible structures on difficult terrain. Yet no detailed record survives to explain how these tasks were accomplished. The possibility that multiple generations of builders reused and modified the same strategic location over centuries adds another layer of complexity to the site's history. Water management presents one of the castle's greatest engineering mysteries. Every successful fortress required a dependable water supply. During a siege, lack of water could prove more dangerous than enemy soldiers. Yet Dinas Bran occupies an isolated summit with no obvious natural spring. Historians and archaeologists continue to debate how the inhabitants secured water. Some propose sophisticated rainwater collection systems. Others suggest hidden storage cisterns or now-lost access routes leading downhill toward water sources. Excavations have produced clues but no definitive solution. The problem becomes even more intriguing when one considers that medieval military planners fully understood the importance of water security. The fact that the castle was built at all suggests that a viable solution existed. The fact that the solution remains unclear today highlights how much practical engineering knowledge has been lost. The defensive design itself raises additional questions. Computer simulations conducted on comparable medieval fortifications show that carefully positioned walls could dramatically increase defensive effectiveness. At Dinas Bran, surviving sections indicate that builders exploited every advantage offered by the terrain. Attackers approaching the summit would have been forced into narrow routes exposed to defenders positioned above. Blind spots appear surprisingly limited. Defensive fields of view overlap efficiently across critical access points. Such optimization suggests a sophisticated understanding of battlefield geometry. Yet no architectural plan survived to explain how these calculations were made. Whether achieved through experience, experimentation, or inherited military traditions, the final result demonstrates a level of practical expertise that remains difficult to quantify. Perhaps the most enduring mystery involves the legends surrounding tunnels beneath the hill. Local folklore speaks of hidden passages extending from the castle into the surrounding landscape. Similar stories appear throughout Britain, often attached to ancient fortifications and castles. Most alleged tunnel networks have never been verified. However, advances in ground-penetrating radar and geophysical surveying have revealed unexpected subterranean structures at numerous archaeological sites around the world. At Dinas Bran, only limited subsurface investigations have been conducted. The possibility that natural cavities, storage chambers, escape routes, or undocumented structures remain concealed beneath the limestone cannot be completely dismissed. Until comprehensive surveys are undertaken, the mystery remains unresolved. Another fascinating question concerns communication. The castle's elevation provided extraordinary visibility across the region. Some researchers have suggested that sites like Dinas Bran may have participated in broader signalling networks using fires, smoke, reflective surfaces, or beacon systems. Across medieval Britain, chains of elevated sites allowed messages to travel rapidly across larger distances. If Dinas Bran formed part of such a network, it would demonstrate a sophisticated understanding of landscape-scale communication. Unfortunately, surviving evidence is insufficient to determine the exact role the fortress may have played. A small stone settlement on the eastern coast of Anglesey was first excavated in the early 20th century and initially appeared to be nothing more than a collection of late Roman and post-Roman ruins. Yet, as archaeologists uncovered its thick walls, carefully planned structures, and evidence of long-term occupation, an unsettling question emerged. How did a relatively isolated community on the edge of the collapsing Roman world construct a settlement whose engineering principles still raise questions today? More than 1,500 years later, Dinligwy remains one of the most overlooked archaeological mysteries in Britain, preserving clues to lost construction methods, environmental engineering, and practical knowledge that vanished long before modern science began documenting such techniques. The first mystery begins with the walls themselves. The settlement is surrounded by massive stone structures built without the extensive use of mortar. In some places, the walls measure nearly 2 meters thick. Such dimensions are surprising for what was once considered a modest farming community. The builder selected and positioned thousands of stones with remarkable precision, creating stable structures capable of surviving centuries of Atlantic storms, seasonal temperature changes, and continuous erosion. Modern engineers understand the principles behind dry stone construction, yet Dinligwy demonstrates a level of durability that remains difficult to explain fully. Many later medieval buildings in Britain suffered severe structural deterioration after only a few centuries. Dinligwy's walls, despite being older, continue to stand. The secret appears to lie in the way the stones were interlocked. Each block contributes to distributing weight throughout the structure, reducing stress concentrations and increasing resistance to movement. Similar principles can be observed at sites such as Machu Picchu and Sacsayhuaman, where stone blocks were arranged to absorb environmental forces without relying heavily on mortar. Yet no written records explain how the builders of Dinligwy learned these techniques. The second mystery involves environmental adaptation. Anglesey experiences strong coastal winds throughout the year. Meteorological records collected in the modern era show that Western Britain is frequently exposed to Atlantic weather systems capable of generating wind speeds exceeding 80 kilometers per hour during severe storms. Despite these conditions, the buildings at Dinligwy appear to have been positioned strategically to reduce direct exposure. Archaeologists have noted that the layout does not seem random. Structures were arranged in ways that minimize the impact of prevailing winds while maximizing shelter within the settlement. Today, Architects use computer simulations and fluid dynamic software to model such effects. The people of Din Ligui possessed none of these tools, yet they achieved results that suggest a sophisticated understanding of local environmental behavior. How this knowledge was accumulated remains uncertain. It may represent centuries of observation passed through generations. Alternatively, it could indicate a formal tradition of construction expertise that disappeared without leaving written evidence. The physical arrangement survives, but the reasoning behind it has been lost. A third mystery concerns drainage and water management. One of the greatest challenges facing any settlement in Western Britain is controlling water. Annual rainfall in parts of Wales can exceed 1,000 millimetres. Without effective drainage, foundations gradually weaken, walls shift and structures collapse. Yet Din Ligui shows signs of remarkable resilience. Excavations suggest that buildings were deliberately placed on slightly elevated ground. Surface runoff appears to have been directed away from key structures through subtle modifications to the landscape. Some researchers believe additional drainage systems may once have existed, but have since been buried beneath centuries of sediment. The challenge facing archaeologists is that only fragments of the original engineering survive. What remains visible today may represent only a portion of a much larger system. Similar situations have occurred elsewhere. At Mohenjo-Daro, excavations revealed sophisticated drainage networks that remained hidden for thousands of years. At Din Ligui, it is possible that future discoveries could reveal comparable solutions adapted to the wet climate of Wales. Another unresolved mystery concerns the source of the settlement's engineering knowledge. Din Ligui was occupied during a period when Roman authority in Britain was weakening. Roman influence had introduced advanced construction techniques, road systems, surveying methods, and organisational practices throughout much of Britain. However, Din Ligui does not fit neatly into either Roman or native British traditions. Certain architectural features resemble local Celtic building styles. Others appear influenced by Roman engineering concepts. The settlement seems to exist in a transitional zone where multiple technological traditions merged. This creates an intriguing possibility. Rather than merely copying Roman methods, the inhabitants may have adapted external knowledge to local conditions, creating hybrid solutions uniquely suited to their environment. If true, Din Ligui represents more than a simple village. It may preserve evidence of technological innovation, occurring during one of the most turbulent periods in British history. The transportation mystery is equally fascinating. Constructing the settlement required moving thousands of stone blocks, many weighing hundreds of kilograms. Today, heavy machinery would simplify such work. 15 centuries ago, every stone had to be quarried, transported, positioned, and secured using human labor and simple tools. The logistics involved are often underestimated. Modern studies of ancient construction projects demonstrate that transporting heavy stone can consume more labor than the actual building process. Experimental archaeology has shown that moving a single 1-ton block using wooden sledges and ropes may require dozens of workers under favorable conditions. Yet evidence for large-scale political authority at Din Ligui remains limited. There are no obvious signs of a powerful ruling class directing enormous workforces. This raises an important question. How was labour organised? Was construction completed gradually over generations? Or did a coordinated effort build much of the settlement within a relatively short period? The archaeological evidence does not provide definitive answers. The stones remain, but the organisational system behind them has disappeared. Another mystery lies in material selection. The builders demonstrated an impressive understanding of local geology. Not all stone performs equally under long-term environmental stress. Some varieties crack under repeated freeze-thaw cycles. Others absorb water and deteriorate rapidly. The survival of Din Ligui suggests careful material choices were made. Builders appear to have selected stone capable of withstanding coastal weather for centuries. This required practical geological knowledge that was likely acquired through experience rather than scientific analysis. Similar patterns appear throughout ancient history. The creators of Roman concrete understood material properties well enough to produce structures that have survived nearly 2,000 years. The engineers of the Inca selected stone types suited to earthquake-prone environments. The builders of Dinligui may have possessed a comparable body of practical expertise, adapted specifically to the Welsh landscape. What do you think? Were the builders of Dinligui simply masters of observation and experience, or did they possess engineering knowledge far more advanced than history has given them credit for? Let us know your thoughts in the comments below. A wooded hillside overlooking the coast of North Wales near the town of Abergele became the site of one of the most ambitious private construction projects of the 19th century. Built between 1810 and 1825 by Lloyd Hesketh Bamford Hesketh, Grich Castle appears at first glance to be a romantic imitation of a medieval fortress. Yet the deeper archaeologists, architects, and engineers have studied the site, the more they have encountered questions that remain surprisingly difficult to answer. Covering roughly 250 acres and incorporating more than 18 towers, extensive curtain walls, underground structures, engineered terraces, and complex drainage systems, the castle represents an extraordinary feat of design and construction. What makes the site fascinating is not simply its scale, but the evidence that its builders solved a series of engineering challenges whose full methods were never properly documented. The first mystery begins with the location itself. Grich was constructed on a steep hillside facing the Irish Sea. Modern surveys show elevation changes of more than 150 meters across parts of the estate. Building on such terrain creates immediate engineering problems. Foundations must be stabilized. Rainwater must be controlled. Slopes must resist erosion. Thousands of tons of stone must be transported uphill. Today, projects on similar terrain often rely on heavy machinery, geotechnical modeling, and computer-generated surveys. Yet the builders of Gurich achieved this more than 2 centuries ago using methods that remain only partially understood. Researchers estimate that tens of thousands of tons of limestone and sandstone were incorporated into the structure. Some blocks weigh several tons each. Historical records describe labourers, horses, and carts, but no detailed engineering documents survive explaining how the largest materials were transported and positioned. This is particularly intriguing because portions of the castle occupy terrain that remains difficult for modern construction vehicles to access. Similar questions have been raised about the transportation logistics behind large 19th century projects such as the construction of the Menai Suspension Bridge in Wales and certain sections of the Caledonian Canal in Scotland. In each case, the physical results survive while much of the practical engineering knowledge has disappeared. One of the most unusual features of Grich Castle is its enormous defensive-looking wall system. Unlike a genuine medieval fortress built for warfare, Grich was never intended to withstand an army, yet its walls extend across large sections of the surrounding hillsides. In some locations, they follow natural ridges with remarkable precision. In others, they traverse areas that would have been almost invisible from the main residence itself. This raises an important question. Why invest so much labour and material into walls that offered little military value? Some architectural historians argue that the walls were purely aesthetic, designed to create the illusion of a medieval landscape. Others suggest they served additional functions. Modern environmental studies have shown that retaining walls can reduce soil movement, redirect runoff, stabilize slopes, and alter wind behavior across a property. If this interpretation is correct, the walls of Gufrich may represent a massive environmental engineering project disguised as architecture. The drainage systems provide another layer of mystery. North Wales receives significant annual rainfall, often exceeding 1,000 millimetres in many coastal regions. Heavy rain combined with steep slopes creates ideal conditions for erosion and structural instability. Yet large portions of Grich Castle survived decades of abandonment before restoration efforts began in the 21st century. Investigations have revealed networks of stone drains, underground channels, culverts, and hidden water management features beneath the estate. Some channels appear designed to intercept runoff before it reached key foundations. Others may have relieved hydrostatic pressure beneath retaining structures. What remains uncertain is the full extent of the system. Parts have collapsed, others remain buried. Even with modern ground-penetrating radar, researchers have yet to produce a complete map of the original drainage network. The situation recalls mysteries surrounding medieval monastic sites such as Valle Crucis Abbey and Fountains Abbey, where sophisticated water management systems remained poorly understood until recent archaeological investigations revealed hidden channels and hydraulic features. Grich may preserve a similar story, though on a much larger landscape scale. Another fascinating mystery involves the castle's mortar and masonry. Grich sits only a short distance from the Irish Sea, exposing the structure to moisture, salt-laden winds, and repeated freeze-thaw cycles. These conditions are notoriously destructive to stone buildings. Modern concrete structures exposed to marine environments often require major repairs within decades. Yet portions of Grich's original masonry have survived for more than 200 years despite prolonged neglect. Laboratory analysis of historic mortars from comparable 19th century structures has shown that traditional lime mortars often possessed properties different from modern cement-based materials. They could absorb moisture, release trapped water, and accommodate structural movement without cracking. Some conservation specialists believe that many traditional recipes incorporated local materials whose exact proportions were never formally recorded. This creates a paradox. Modern engineering possesses vastly superior analytical tools, yet restoration teams frequently struggle to reproduce the long-term performance of historic masonry. The builders may not have understood chemistry in modern scientific terms, but they possess practical knowledge accumulated through generations of experience. Wind behavior presents another engineering puzzle. Grich Castle occupies an exposed position overlooking the sea, where storms can generate powerful gusts. Yet studies of the site's layout suggest that many principal structures occupy surprisingly sheltered positions. Certain towers appear to deflect prevailing winds. Some courtyards create protected microclimates. Long walls may function as windbreaks. Today, engineers use computational fluid dynamics software to model airflow around buildings. The designers of Grich had no such tools. Nevertheless, the arrangement of structures across the estate appears optimized in ways that suggest extensive practical understanding of local environmental conditions. Whether this resulted from deliberate planning or centuries of accumulated architectural tradition remains unclear. Beneath the visible structures lies another mystery. Historical documents refer to service tunnels, storage chambers, cellars, and underground passages. Over time, collapses, vegetation, and neglect obscured many of these features. Modern surveys have identified subsurface voids in multiple locations, suggesting that portions of the underground infrastructure remain undiscovered. The existence of hidden spaces raises important questions about the castle's original operation. How were supplies moved through the estate? Were some tunnels connected to drainage systems? Did underground routes allow servants to move unseen between key locations? Without comprehensive excavation, many answers remain unknown. The broader mystery concerns knowledge itself. Grich Castle required expertise in surveying, geology, hydrology, transportation masonry, materials science, logistics, and landscape engineering. Every tower, retaining wall, drainage channel, and foundation reflects decisions made by builders who understood their environment in extraordinary detail. Yet almost none of the technical knowledge survives in complete form. No comprehensive engineering manuals explain how the slopes were stabilized. No detailed records reveal how water systems were designed. No documents describe the precise calculations behind retaining structures or wall alignments. The physical evidence remains, but the intellectual framework that created it has largely vanished. A grassy depression on the edge of Caerleon, Wales, attracted antiquarian attention for centuries before systematic archaeological excavations in the 19th and 20th centuries revealed its true identity as one of the best preserved Roman military amphitheatres in Britain. Built around AD 90 beside the fortress of the Second Augustan Legion, the structure could hold approximately 6,000 spectators. At first glance, it appears to be simply another Roman arena. Yet beneath its grassy banks lies a collection of engineering mysteries that continue to challenge archaeologists, architects, and historians. Nearly 2,000 years after its construction, researchers still debate how Roman engineers achieved such remarkable performance in acoustics, drainage, earthwork stability, logistics, and large-scale construction without leaving behind detailed technical manuals. The first mystery begins with the amphitheatre's location itself. Wales is not the sort of environment where large earthworks should survive easily for nearly 2 millennia. The region receives significant rainfall throughout the year, creating conditions that encourage erosion, waterlogging, and structural instability. Modern civil engineers understand that large earthen embankments require careful calculations involving soil density, moisture content, drainage gradients, and load distribution. Yet Roman engineers constructed enormous seating banks capable of supporting thousands of people while maintaining stability for centuries. Archaeological studies indicate that the seating areas were created using carefully layered earth and rubble deposits, compacted in stages. What remains unclear is exactly how Roman builders determined the correct mixture of materials and compaction techniques. No surviving Roman document explains the engineering procedures used at Caerleon. The structure simply exists as evidence that the knowledge once existed. The scale of the earthworks becomes even more impressive when compared with other ancient construction projects. The amphitheatre measures approximately 86 metres by 73 metres, making it one of the largest Roman arenas in Britain. Moving and compacting the enormous volume of soil required would have demanded a highly organised workforce. Modern estimates suggest that thousands of cubic metres of material were transported, positioned, and compacted during construction. Unlike modern builders, Roman engineers had no bulldozers, excavators, or hydraulic compactors, yet they successfully created embankments that have survived longer than many 19th century engineering projects. The question is not whether they possessed the necessary knowledge. The question is how they acquired it and why so little documentation survives. Another mystery concerns the amphitheatre's remarkable acoustics. Roman architects repeatedly demonstrated an ability to create venues where speech could travel surprising distances. Similar effects can be observed in structures such as the Roman theatres Orange in France and Aspendos in Turkey. Caerleon presents a particularly interesting case because much of the original stone seating has disappeared, leaving primarily the earthworks behind. Nevertheless, studies of the arena's geometry suggest that the elliptical design helped concentrate and distribute sound efficiently. A person standing near the center could potentially be heard by spectators seated around the arena without any amplification technology. Modern acoustic engineers can model such effects using sophisticated computer simulations, yet Roman builders achieved them through practical experience and empirical design. Whether they fully understood the underlying physics remains unknown. The drainage system represents another engineering puzzle. Rainfall has always posed a major threat to open-air arenas. Without effective drainage, the central arena would quickly become unusable. Excavations have revealed evidence of underground drains and water management features beneath the amphitheatre. Some sections continue to function surprisingly well despite their age. Roman engineers throughout the empire displayed exceptional expertise in hydraulic engineering. Their aqueducts carried water across vast distances with gradients often measured in only a few centimeters per kilometer. At Caerleon, however, the challenge was the opposite. Instead of transporting water in, they needed to remove it efficiently from a rain-soaked environment. Archaeologists still do not possess a complete map of the original drainage network. Portions remained buried, damaged, or lost entirely. The surviving evidence demonstrates sophisticated planning, but leaves many questions unanswered regarding the full design. Perhaps even more fascinating is the relationship between the amphitheatre and the military fortress it served. Caerleon was not merely a civilian settlement, it was one of the most important Roman military bases in Britain, housing thousands of legionaries. The amphitheatre stood outside the fortress walls, yet remained closely connected to military life. Historians traditionally interpret the structure as a venue for training exercises, public ceremonies, entertainment, and displays of military skill. However, certain architectural features suggest that its role may have been more complex. Subterranean passages and service corridors indicate a carefully organized movement system beneath the arena. These spaces allowed participants, animals, equipment, and performers to enter and exit efficiently. Yet archaeologists continue to debate whether all of these underground areas have been identified. Geophysical surveys have detected anomalies beneath the site that may indicate additional buried structures still awaiting excavation. The mystery deepens when considering the speed at which Roman construction projects could be completed. Building an amphitheatre capable of holding 6,000 spectators required surveying, excavation, earth-moving drainage installation, structural reinforcement, and architectural planning. Modern project managers understand the complexity of coordinating such operations. Roman engineers achieved similar results repeatedly across Europe, North Africa, and the Middle East. The Colosseum in Rome, capable of holding tens of thousands of spectators, was completed in less than a decade. Although Caerleon was much smaller, the same organizational principles appear to have been at work. The empire's ability to mobilize labor, materials, and expertise remains one of the great logistical achievements of the ancient world. Yet the administrative systems that made such efficiency possible are only partially understood. Excavations have also revealed evidence suggesting that the amphitheatre visible today represents only a fraction of the original complex. Archaeological investigations conducted over many decades uncovered entrances retaining structures and internal features that had been hidden beneath accumulated soil. More recent geophysical surveys have identified additional subsurface anomalies. Ground-penetrating radar and magnetometry can detect buried structures without excavation, and several unexplained features remain under investigation. Some researchers suspect that associated buildings once surrounded the arena, serving administrative, military, or ceremonial functions. Others argue that certain anomalies may simply reflect later modifications. Until further excavations occur, these questions remain unresolved. The survival of the amphitheatre also raises questions about Roman material science. Ancient builders selected specific combinations of soil, stone, timber, and drainage materials capable of enduring centuries of environmental stress. Similar mysteries surround Roman concrete, whose durability continues to attract scientific attention. Studies published in recent years have shown that Roman concrete sometimes developed self-healing properties through chemical reactions involving lime clasts and water infiltration. Although Caerleon relies more heavily on earthworks than concrete, the same broader principle applies. Roman engineers repeatedly produce structures whose longevity exceeds expectations. Their success suggests a practical understanding of materials that modern researchers are still attempting to reconstruct. The amphitheatre's role in Roman Britain introduces another layer of mystery. Historical records concerning the site are limited. Archaeological evidence provides valuable clues, yet many details of daily operations remain uncertain. How frequently were events held? What kinds of spectacles took place? How were large crowds managed? How were performers and animals transported through the underground passages? The physical structure provides partial answers, but the complete picture remains elusive. Every excavation uncovers new information while simultaneously revealing new gaps in our understanding. Northern Portugal, Porto District. Hidden beneath modern towns, vineyards, river valleys, and granite hills lies a network of ancient settlements dating back more than 2,000 years. Archaeological excavations at sites such as the Castro of Monte Castello and various Roman occupation layers around Porto have revealed evidence of fortified hilltop communities, advanced water systems, metallurgy, and long-distance trade networks that connected the Atlantic coast to the wider Mediterranean world. The first major discoveries emerged through archaeological surveys and excavations conducted throughout the 20th century, uncovering defensive walls, imported ceramics, metalworking remains, hydraulic structures, and multiple occupation layers spanning the Iron Age, Roman period, and Middle Ages. What researchers expected to find were isolated tribal settlements. What they discovered instead was evidence of engineering knowledge whose full complexity remains difficult to explain. One of the earliest questions concerns location itself. Many ancient settlements throughout Porto District occupy elevated granite hills with commanding views of valleys, rivers, and transportation corridors. Sites such as Monte Castello appear positioned with extraordinary strategic precision. Today, military planners use satellite imagery, digital terrain models, and geographic information systems to identify optimal defensive positions. Yet Iron Age communities achieved remarkably similar results more than 2 millennia ago. From many of these hill forts, visibility extends across vast areas of surrounding terrain, and researchers have noted that numerous settlements maintained visual contact with neighboring fortified sites, potentially creating communication networks spanning large regions. The question is simple but profound. How were these locations selected so accurately without modern surveying equipment? Some scholars argue that generations of accumulated local knowledge provided the answer, while others suggest that ancient communities possess sophisticated observational techniques that remain poorly understood. The mystery becomes even more intriguing when compared with other ancient hilltop fortifications around the world. Similar patterns appear at Celtic oppida across Europe, Inca strongholds in Peru, and Iron Age settlements in Britain. Different cultures, separated by geography and time, repeatedly identified nearly identical strategic solutions. Northern Portugal sits upon some of the hardest granite formations in Western Europe. Granite presents enormous engineering challenges even today, requiring modern quarrying operations equipped with diamond-tipped cutting equipment, heavy machinery, and significant energy expenditure. Yet ancient builders across Porto District transformed these landscapes on a remarkable scale. Archaeologists have documented extensive defensive walls, carefully shaped stone platforms, terraced slopes, and large-scale modifications of natural terrain. Some fortification walls contain thousands of tons of stone, while entire sections of hillsides were leveled to create habitable surfaces. The challenge is not simply understanding how these stones were moved, but how such massive projects were organized. Experimental archaeology has demonstrated that moving a single block weighing 1 ton using only ancient technology can require dozens of workers. Yet many sites contain hundreds or even thousands of similar stones. Without written engineering manuals, researchers must reconstruct construction methods from physical evidence alone. Every excavation reveals the achievement, but none reveal the complete process. Excavations have produced evidence that Porto District was far more connected to the ancient world than previously believed. Imported ceramics, luxury goods, metal objects, and trade materials originating from distant regions have been identified at multiple sites. Some artifacts trace connections to southern Iberia, others suggest links with Roman Italy, and still others indicate trade routes extending across the western Mediterranean. Distances involved often exceeded 1,000 kilometers. Such discoveries challenge traditional assumptions regarding the isolation of Atlantic communities. The common image portrays Iron Age populations as relatively disconnected tribal societies, yet archaeological evidence increasingly paints a different picture. Researchers now believe portions of northern Portugal may have participated in commercial networks stretching from the Atlantic Ocean to North Africa and beyond. This raises a major logistical mystery. How are such long-distance supply chains maintained? Without modern ports, navigation systems, maps, or communication technologies, ancient traders managed exchanges across enormous distances. The organizational systems behind these networks remain only partially understood. Among all technological puzzles found in Porto District, none may be more fascinating than water management. Water is deceptively simple. Every civilization needs it, yet controlling water on a large scale has always been one of humanity's greatest engineering challenges. Archaeological investigations throughout northern Portugal have uncovered evidence of Roman hydraulic systems, reservoirs, drainage channels, cisterns, water distribution networks, and engineered conduits. At first glance, these structures appear ordinary, but closer examination tells a very different story. For water to flow efficiently through a channel, engineers must maintain extremely precise gradients. A slope that is too steep accelerates erosion and damages infrastructure, while a slope that is too shallow prevents reliable flow. Modern engineers solve such problems using laser levels, total stations, satellite positioning, and computer modeling. Roman engineers possessed none of these technologies, yet many surviving hydraulic systems demonstrate astonishing precision. In some Roman aqueducts across the empire, average gradients were maintained at less than 1 meter per kilometer, while certain sections achieved accuracies measured in mere centimeters over hundreds of meters. The engineering principles required for such precision remain astonishing. Researchers know that Roman surveyors used instruments such as the chorobates and groma, but exactly how these tools were employed to achieve such consistency remains debated. The mystery deepens when considering maintenance. Water systems must function continuously despite seasonal rainfall changes, sediment accumulation, structural movement, and erosion. Many hydraulic structures discovered in Portugal continued functioning for centuries, and some survived nearly 2,000 years. Even more puzzling is the apparent transfer of hydraulic knowledge between generations. The engineers who designed these systems are long gone. Their technical manuals have largely disappeared. Their training methods remain unknown, and their calculations were never preserved. What survives is the infrastructure itself. This creates one of archaeology's most frustrating paradoxes. The physical evidence proves the technology existed, but the knowledge explaining exactly how it worked has largely vanished. Similar mysteries appear elsewhere in the ancient world. Roman aqueducts in Spain, underground Qanat systems in Persia, the water channels of Machu Picchu, and the hydraulic works of Petra all demonstrate levels of precision that continue to impress modern engineers. Porto District belongs to that same tradition of forgotten expertise. The water still tells the story, but the engineers do not. Excavations have uncovered slag deposits, furnace remains, metal tools, and evidence of extensive ironworking activity. To modern observers, iron production may seem straightforward, but in reality it is an extraordinarily demanding technological process. Producing workable iron requires temperatures approaching 1200 degrees Celsius. Achieving such temperatures consistently demands precise control of airflow, fuel quality, furnace geometry, and ore composition. Even small variations can drastically affect results. The archaeological evidence suggests that ancient metal workers in northern Portugal mastered these variables remarkably well. Large quantities of slag indicate sustained industrial-scale production rather than occasional local manufacturing. Experimental archaeologists attempting to recreate ancient furnaces often discover that apparently simple designs conceal highly sophisticated engineering principles. Airflow dynamics, combustion efficiency, thermal retention, and material selection all interact in complex ways. Many of the practical techniques that ancient metalworkers relied upon may never have been written down. Instead, they were likely transmitted through apprenticeship systems that disappeared centuries ago. Remains of the Dolgarrog Dam disaster, located in the Conwy Valley of North Wales, mark the site of one of Britain's most devastating engineering failures. The disaster occurred on November 2, 1925, when the upper reservoir of the Dolgarrog hydroelectric scheme suddenly collapsed, releasing an estimated 2 billion gallons of water, more than 9 billion litres, into the valley below. The flood raced toward the village of Dolgarrog, destroying homes, bridges, railway infrastructure, and industrial facilities within minutes. Official records documented 16 deaths, although many historians believe the toll could have been far higher had the disaster occurred during the day rather than shortly after midnight. More than a century later, the remains of the failed dam continue to raise questions that engineers, geologists, and historians have never fully answered. The first mystery concerns the exact mechanism that triggered the collapse. Official investigations concluded that exceptionally heavy rainfall filled the reservoir beyond safe levels. However, the explanation was never entirely satisfactory. Rainfall alone rarely destroys a properly designed dam. Modern engineering studies suggest that the rainfall event was merely the final trigger in a chain of hidden failures that may have been developing for years beneath the structure. One of the most intriguing mysteries involves the geology beneath the reservoir. The dam was constructed in a mountainous region dominated by ancient volcanic rocks, fractured bedrock, and natural fault systems. At the time of construction, geological surveys were far less sophisticated than modern investigations. Engineers lacked ground-penetrating radar, satellite imaging, computerized geological models, and advanced subsurface scanning technologies. As a result, much of what existed beneath the foundation remained unknown. Some modern researchers believe that water gradually infiltrated natural fissures hidden within the underlying rock formations. Over time, this seepage may have enlarged existing fractures through a process known as internal erosion. Laboratory studies show that water moving through microscopic cracks can slowly transport sediment particles away from supporting structures. Initially, the process is invisible. Eventually, the erosion creates underground channels large enough to compromise the stability of entire foundations. Similar mechanisms have contributed to dam failures around the world, including several major reservoir disasters during the 20th century. What makes Dolgarrog particularly mysterious is that no one knows how long such erosion may have been occurring. Was it developing for a decade? For a year? Or did it begin shortly after construction was completed? The surviving evidence cannot provide a definitive answer. The second mystery centers on the extraordinary speed of the collapse. Witness accounts describe the failure as sudden and catastrophic. Yet modern structural engineering suggests that large failures are often preceded by warning signs. tiny movements, increasing seepage rates, unusual water pressure changes, and microscopic cracking typically occur before complete structural collapse. Today, engineers monitor major dams using instruments capable of detecting movements measured in fractions of a millimeter. Satellite-based interferometric radar can identify ground deformation across entire landscapes. Fiber optic sensors can track internal stresses in real time. None of these technologies existed in 1925. The question remains, did Dolgarrog provide warnings that nobody recognized? Some engineers argue that subtle indicators likely existed but went unnoticed because the technology required to detect them had not yet been invented. Others believe the final failure may have occurred so rapidly that even modern monitoring systems would have provided little opportunity for intervention. A third mystery involves the reservoir's drainage and overflow capacity. Every dam must safely manage extreme inflows during periods of intense rainfall. Engineers design spillways to release excess water before dangerous pressures accumulate. Yet historical records suggest that the rainfall preceding the disaster was among the heaviest experienced in the region for many years. Meteorological reconstructions indicate that parts of North Wales received exceptionally high precipitation during the days before the collapse. However, debate continues regarding whether the spillway system was fundamentally inadequate or whether an entirely different failure mechanism bypassed the intended safety systems. Modern hydraulic modelling produces conflicting results. Some simulations suggest that overtopping alone could have initiated structural damage. Other models indicate that overtopping should not have been sufficient to destroy the dam unless hidden weaknesses already existed within the foundation. The discrepancy highlights a frustrating reality. Even with 21st century computational tools, researchers cannot fully reconstruct every condition present on the night of the disaster. Another unresolved question concerns the engineering assumptions used during construction. The Dolgarrog hydroelectric project represented advanced technology for its era. Hydroelectric power was transforming industries across Europe, and engineers were increasingly confident in their ability to reshape landscapes through reservoirs, tunnels, pipelines, and generating stations. Yet engineering history repeatedly demonstrates that confidence can exceed knowledge. Similar lessons emerged decades later during the failures of the Malpasset Dam in France in 1959 and the Vajont Dam disaster in Italy in 1963. In both cases, structures built using sophisticated engineering principles encountered geological conditions that designers had not fully understood. The comparison is striking. At Malpasset, hidden weaknesses within the bedrock contributed to catastrophic failure. At Vajont, an enormous landslide generated a massive wave that overwhelmed the reservoir system, despite the dam itself remaining largely intact. These events demonstrated that geology can be as important as engineering design. Dolgarrog may represent an earlier example of the same principle. The fourth mystery involves the flood itself. Investigators estimated that billions of gallons of water surged into the valley within a very short period. The resulting flood wave moved with extraordinary force. Entire buildings were swept away. Heavy industrial equipment was displaced. Railway infrastructure suffered severe destruction. Hydraulic calculations indicate that floodwaters traveling through narrow valleys can accelerate dramatically due to topographic constriction. As water is forced through limited space, velocity increases while destructive energy rises exponentially. Modern studies of dam break floods show that flow velocities can exceed several meters per second, generating forces capable of moving vehicles, trees, and large structural components. Yet even today, estimates of the exact flood characteristics at Dolgarrog vary considerably. Different models produce different peak flow rates and flood heights. This uncertainty means that some aspects of the disaster remain scientifically unresolved more than 100 years later. Perhaps the most fascinating mystery lies in the physical remains themselves. Fragments of the failed structure continue to provide evidence for modern investigation. Laser scanning, photogrammetry, geological mapping, and digital reconstruction have allowed researchers to study details that previous generations could not examine. Paradoxically, every new analysis seems to create additional questions. Some models suggest the structure should have survived. Others indicate that relatively small defect could have triggered progressive collapse. The competing conclusions reveal how difficult it is to reconstruct historical engineering failures when critical data has been lost. And that leads to the greatest mystery of all, the disappearance of knowledge. Many original construction records no longer survive. Detailed geological observations were never recorded or have been lost. Instrumentation data did not exist. Engineers left behind physical structures, but only fragments of the information needed to fully understand them. The ruins of Michelsberg stand on a steep hill in the forest of Baden-Württemberg, Germany, where centuries of wind, rain, and war have erased most traces of its builders. Yet one question remains. How did medieval engineers create a fortress so durable that parts of it survived hundreds of years after its destruction, using techniques that historians still cannot fully explain? Located near the Upper Rhine region of southern Germany, Michelsberg has attracted archaeological attention for decades. Excavations, historical records, masonry analysis, and modern topographic surveys have gradually revealed fragments of the fortress. But with much of the structure lost, every discovery has generated new questions rather than definitive answers. The first puzzle begins with the location itself. Michelsberg was constructed on elevated terrain that provided extraordinary visibility across surrounding valleys and transportation routes. Modern digital terrain analysis shows that the site commands an exceptional defensive position, allowing observers to monitor movement from multiple directions. Choosing a strategic location is one thing, but building there is another. Every stone block, timber beam, tool, and supply had to be transported uphill without modern machinery. Historians estimate that medieval hilltop fortifications often required thousands of tons of construction material, and even a modest fortress could consume several thousand cubic meters of stone. The challenge becomes easier to understand when compared with later engineering projects. During the construction of many 18th century European fortifications, cranes, improved roads, and advanced transport systems were available, yet the builders of Michelsberg possessed none of these advantages. Somehow, they managed to organize logistics on a scale that remains difficult to reconstruct today. No surviving engineering manuals explain how materials were transported, and no construction plans describe lifting mechanisms. The physical evidence demonstrates the achievement, but the process behind it remains largely invisible. One of the most overlooked mysteries concerns measurement. Long before satellites, aerial photography, or GPS technology, the builder selected a location that appears remarkably optimized for defense. Modern survey equipment can calculate visibility corridors within seconds, while medieval engineers had only their eyes, simple measuring tools, and accumulated experience. Archaeologists studying hilltop fortifications throughout Europe have repeatedly observed evidence of surprisingly accurate terrain assessment. Similar patterns appear at Hohensalzburg Fortress in Austria, Crac des Chevaliers in Syria, and numerous German mountain castles. The question is how? How did engineers identify the ideal location among hundreds of potential hilltops? How did they calculate lines of sight across valleys extending several kilometers? How did they determine the most effective positions for defensive walls before construction even began? No written records survive to answer these questions. The accuracy visible at Michelsberg suggests a practical surveying tradition far more sophisticated than many modern observers assume. Perhaps the most important engineering decision in any fortress is invisible: the foundations. The remains of Michelsberg indicate that builders integrated parts of the structure directly into the underlying bedrock. This strategy dramatically increases stability by reducing settlement and distributing structural loads more effectively. Modern geotechnical engineers perform extensive testing before placing major structures on rocky terrain, analyzing fracture zones, stress patterns, groundwater movement, and rock strength. Medieval builders possessed no laboratory equipment, yet many of their choices appear surprisingly effective. Several surviving sections remain stable despite centuries of freeze-thaw cycles. In southern Germany, winter temperatures regularly fluctuate around freezing, creating conditions that can slowly destroy masonry through repeated expansion and contraction. The persistence of these foundations raises an important question. Did medieval builders possess empirical geological knowledge that has largely disappeared from historical records, or were generations of accumulated experience sufficient to produce engineering results that today appear almost scientific? Among all the mysteries surrounding Michelsberg, none may be more intriguing than the material that held the fortress together. Mortar rarely attracts public attention, yet throughout history some of humanity's most durable structures owe their survival not to stone, but to the substances binding the stone together. The Roman Empire created hydraulic concretes capable of surviving nearly 2,000 years in marine environments, and modern studies have revealed that Roman builders sometimes incorporated volcanic ash and lime mixtures that produce self-healing chemical reactions. Michelsberg presents a smaller but equally fascinating puzzle. Fragments of surviving masonry suggest that the mortar used in parts of the fortress possessed remarkable durability relative to its age and environmental exposure. Even where walls have collapsed, researchers have observed sections where the bond between stones remained unexpectedly strong. The mystery deepens because medieval mortar recipes varied dramatically between regions. Traditional lime mortar was common throughout Europe, but local builders frequently modified mixtures using materials such as crushed brick, ceramic fragments, sand of varying grain sizes, charcoal residues, animal products, plant fibers, and other additives. At Michelsberg, some analyses indicate compositional characteristics that do not perfectly match standard regional formulations documented elsewhere. This raises several possibilities. Perhaps builders discovered a local source of mineral-rich aggregate that improved durability. Perhaps they intentionally modified the mixture using organic additives whose chemical traces have largely disappeared. Perhaps knowledge was transferred through traveling craftsmen whose techniques were never documented. Experimental archaeology has demonstrated that small changes in mortar composition can significantly affect strength, water resistance, flexibility, and long-term durability. Even today, restoration specialists often struggle to reproduce historical mortars exactly because centuries of chemical alteration can obscure their original composition. In other words, the fortress may still contain a technological secret hidden within microscopic mineral structures. The stones remain visible, but the recipe does not. A fortress cannot survive without water, and this simple fact creates another major puzzle. Michelsberg occupies elevated ground far above major water sources. During peacetime, transporting water uphill would have been difficult enough. During a siege, it could become catastrophic. Many medieval fortifications solved this problem through sophisticated engineering. Some built deep wells reaching groundwater hundreds of feet below the surface, while others constructed rainwater collection systems connected to underground cisterns. Some combined both methods. At Michelsberg, evidence suggests that water management systems likely existed, but much of the infrastructure has disappeared. Without a reliable water supply, the fortress could not have functioned effectively. Yet without surviving documentation, archaeologists can only reconstruct fragments of the original system. Another unanswered question lies underground. Throughout Europe, archaeologists have repeatedly discovered forgotten chambers, storage facilities, escape tunnels, and buried foundations beneath ruined castles. Modern technologies such as ground-penetrating radar, electrical resistivity surveys, and laser mapping have transformed the search for hidden structures. At several medieval sites, these techniques have revealed architectural features completely invisible from the surface. Some surveys around Michelsberg have identified subsurface anomalies that remain insufficiently investigated. Are they natural geological formations, collapsed storage rooms, or buried foundations? No one knows for certain. Future excavations may reveal that much of the fortress still exists beneath the ground. Perhaps the greatest mystery is not the fortress itself, but the disappearance of the knowledge that created it. The builders of Michelsberg demonstrated competence in logistics, surveying, structural engineering, geology, water management, and defensive planning. Yet almost none of their technical reasoning survives. No complete construction plans exist. No engineering manuals explain their methods. No records describe how foundations were designed, and no documents reveal how mortar recipes were formulated. Modern archaeologists can scan ruins with lasers accurate to millimeters, engineers can model structures using powerful computers, and chemists can analyze ancient materials at microscopic levels. Even so, many of the decisions made by Michelsberg's builders remain difficult to explain fully. The fortress itself has largely vanished, but the engineering questions have not. What do you think? Were the builders of Michelsberg simply masters of experience and observation, or did they possess engineering knowledge far more advanced than history has given them credit for? Let us know your thoughts in the comments below. Rugged cliffs along the coast of Pembrokeshire, Wales, overlooking the Irish Sea, preserve the remains of what appears to be a modest medieval religious site associated with St Non, the mother of St David, the patron saint of Wales. Beside the ruins lies a freshwater spring known as St Non's Well. Archaeological investigations conducted throughout the 20th and 21st centuries reveal that the location was far more complex than a simple religious monument. Beneath the surviving ruins lies evidence of centuries of occupation, repeated rebuilding phases, sophisticated site selection, and engineering decisions that continue to raise questions. While the chapel itself appears modest, the technical knowledge required to establish and maintain a permanent sacred complex on one of the most exposed coastlines in Britain remains surprisingly difficult to explain. The first mystery begins with location. The chapel stands on cliffs more than 50 meters above sea level, directly exposed to Atlantic storms that can generate wind speeds exceeding 100 kilometers per hour during severe winter weather. Modern coastal engineers generally avoid placing long-term structures in such environments unless there are compelling strategic reasons. Yet medieval builders deliberately selected this exact position. The site combines three unusual characteristics rarely found together: a stable rock platform, a freshwater spring, and an extensive view across maritime routes. Geological studies show that the underlying bedrock consists primarily of Cambrian formations dating back over 500 million years. These rocks provide a relatively stable foundation compared to surrounding coastal sediments. The question is how medieval builders identified the most suitable location without modern geological surveys. Similar mysteries surround sacred sites such as Machu Picchu and Delphi, where ancient builders selected locations that modern studies later revealed to possess unusual geological advantages. At Chapel of St Non, the precision of the site choice suggests a level of environmental understanding that was never recorded. The second mystery involves the freshwater spring itself. St Non's Well remains one of the most remarkable features of the site. Despite its proximity to the sea, the water remains fresh rather than saline. Hydrologically, this is not impossible, but maintaining a reliable freshwater source near an exposed coastline requires a very specific geological configuration. Groundwater must move through permeable rock layers while remaining protected from saltwater intrusion. Modern hydrogeologists use extensive mapping, drilling, and monitoring equipment to identify such systems. Medieval builders possessed none of these technologies, yet they not only discovered the spring but built an enduring religious complex around it. Similar sacred springs appear throughout Britain, Ireland, and continental Europe, suggesting that ancient populations possessed highly refined methods for locating reliable groundwater. Exactly how they achieved this remains unclear. No manuals survive explaining the techniques used to identify these water sources. The third mystery concerns water management. Wales receives an average annual rainfall ranging from 1,000 to more than 3,000 millimeters depending on location. Coastal Pembrokeshire experiences frequent storms and persistent moisture. Under such conditions, poorly designed sites quickly become waterlogged. Yet archaeological observations indicate that the chapel and spring area remained usable for centuries. This suggests that the builders understood local drainage patterns in considerable detail. Water naturally flowed away from key structures rather than accumulating around them. Similar engineering principles can be observed at medieval sites such as Valais Crucis Abbey, where drainage systems continue to function after more than 700 years. However, much of the original infrastructure at Chapel of St. Non has disappeared, leaving researchers uncertain whether artificial channels, buried drains, or carefully selected terrain provided the solution. Whatever method was used, it worked exceptionally well. Another puzzle involves the building materials themselves. The coastal environment is notoriously destructive. Salt spray accelerates stone weathering. Moisture penetrates masonry. Repeated freeze-thaw cycles gradually fracture walls. Modern coastal structures often require significant maintenance within decades, yet portions of Chapel of St. Non survived for centuries. Archaeologists studying medieval construction in Wales have identified lime-based mortars containing complex mixtures of sand, shell fragments, and organic additives. In some cases, these mortars display remarkable durability. Recent material analyses of medieval lime mortars elsewhere in Britain have revealed microscopic crystalline structures that contribute to self-healing behavior, allowing small cracks to reseal over time. Whether the builders of Chapel of St. Non intentionally exploited similar properties remains unknown. No written records describe their recipes. The structure itself may preserve evidence of material technologies that were once common but are now largely forgotten. The fifth mystery involves what is missing rather than what survives. Excavations suggest that the visible ruins represent only part of a larger historical complex. Researchers believe additional buildings once stood nearby, potentially including accommodation for pilgrims, storage structures, boundary walls, and service buildings. Yet coastal erosion has removed portions of the archaeological record. Every year, waves and weather continue to reshape the cliffs. This creates an unusual challenge. Archaeologists may be investigating a site that is literally disappearing while it is being studied. Similar situations have occurred at coastal heritage locations throughout Britain, where erosion rates sometimes exceed 0.5 meter per year. At Chapel of St. Non, important clues regarding construction techniques, site organisation, and daily operations may already have been lost to the sea. Perhaps the most intriguing mystery concerns landscape alignment. The chapel, spring, pathways, and surrounding topography appear integrated into a carefully selected setting. Researchers have noted that many sacred sites across Britain occupy locations combining water sources, elevated views, stable geology, and visibility from major travel routes. Individually, these features are common. Together, they become statistically unusual. Chapel of St. Non follows this pattern almost perfectly. Whether this reflects practical engineering decisions, religious symbolism, accumulated local knowledge, or a combination of all three remains debated. Ancient builders repeatedly selected landscapes that modern analysis reveals to be exceptionally functional. The process by which they identified these locations remains poorly understood. The site also raises questions about knowledge transmission. Constructing and maintaining a functioning religious centre required expertise in surveying, foundation preparation, stoneworking, drainage, resource management, and environmental observation. Such skills are rarely acquired by chance. They normally emerge through generations of accumulated experience. Yet almost none of the technical documentation survives. No construction plans exist. No engineering manuals explain how foundations were positioned. No written instructions describe how builders evaluated ground stability or managed water flow. This absence of information creates a paradox frequently encountered in archaeology. The physical achievements remain visible, but the intellectual framework that produced them has largely vanished. Mynyddig Garreg Tower stands on elevated ground in Carmarthenshire, southwest Wales. Unlike famous medieval castles that attract thousands of visitors each year, this isolated structure remains largely overlooked. Archaeological surveys and historical records have identified the tower as part of a defensive and observation network that once overlooked important routes across the Welsh landscape. Yet, despite its modest appearance, the site presents a series of engineering mysteries that remain surprisingly difficult to explain. What appears today as a simple stone ruin may actually preserve evidence of sophisticated knowledge involving surveying, logistics, structural engineering, weather resistance, and communication systems. The tower's surviving remains continue to raise questions that archaeologists, historians, and engineers have not fully answered. The first mystery begins before a single stone was ever placed. Building a tower on a hill sounds simple. In reality, selecting the optimal location without modern technology is an extraordinarily complex task. Modern military planners use satellite imagery, geographic information systems, and computer-generated visibility models to determine the best observation points. The builders of Mynyddig Garreg had none of these tools, yet the tower occupies a position that provides extensive visibility across the surrounding countryside. From elevated points such as this, observers could monitor movement over many kilometers in multiple directions. Modern viewshed analysis demonstrates that even small differences in elevation can dramatically affect visibility. A hilltop only 20 meters lower may lose sight of critical sections of surrounding terrain. Somehow, the builders identified one of the most strategically effective positions available. This mystery appears throughout history. The builders of Iron Age hill forts, Roman signal stations, and Inca mountain outposts repeatedly selected locations that modern computer analysis later confirmed were exceptionally advantageous. How ancient surveyors accomplished this with limited instruments remains uncertain. Some researchers suggest years of observation and accumulated local knowledge. Others believe surprisingly advanced surveying techniques may have been employed. Whatever the answer, the placement of Mynyddig Garreg Tower demonstrates an understanding of the landscape analysis that exceeded what many people assume for medieval builders. Wales is not a forgiving place for stone structures. The region receives some of the highest rainfall totals in the United Kingdom. Atlantic weather systems bring powerful winds, frequent storms, and constant moisture. Freeze-thaw cycles further accelerate deterioration by forcing water into microscopic cracks where expanding ice gradually breaks stone apart. Modern engineers spend enormous resources protecting structures from these effects. Waterproof membranes, reinforced concrete foundations, drainage systems, and corrosion-resistant materials are standard requirements. The builders of Myned y Garreg possessed none of these technologies, yet portions of the structure survived centuries of exposure. This raises important questions about the engineering methods used during construction. The builders understood that water represents one of the greatest threats to any stone building. Effective drainage was essential, foundation placement had to account for soil movement, and walls had to withstand repeated wind loading year after year. Studies of medieval Welsh fortifications have shown that many builders intentionally selected local stone varieties based on weather resistance rather than convenience alone. In some cases, surviving masonry demonstrates a remarkable understanding of structural stability, despite the absence of formal engineering science. Myned y Garreg may preserve evidence of similar practical knowledge, much of which disappeared long ago. One of the most overlooked questions concerns transportation. Every stone visible in the tower had to be extracted, transported, lifted, positioned, and secured. Even relatively small stone towers may require hundreds of tons of material. Moving such quantities across steep terrain presents a major logistical challenge. Today, cranes, trucks, and hydraulic equipment perform these tasks. Medieval builders relied on manpower, animals, ropes, sledges, rollers, and simple lifting mechanisms. Archaeologists studying construction projects throughout Britain have repeatedly encountered the same puzzle. Historical records rarely explain how large quantities of stone were moved efficiently. Experiments have demonstrated that teams of workers using wooden sledges can transport surprisingly heavy loads. However, the labor requirements remain immense. A single stone weighing several tons could require dozens of individuals working in coordination. Comparable mysteries exist at sites throughout the world. The builders of Stonehenge transported stones weighing up to 25 tons. The engineers of Machu Picchu moved massive blocks across mountainous terrain. The creators of the Moai statues on Easter Island relocated monuments weighing more than 80 tons. Although Myned y Garreg is smaller in scale, it belongs to the same category of logistical mystery. The surviving structure represents not merely construction, but the successful organization of a large workforce operating without modern machinery. Perhaps the most fascinating possibility involves communication. Many elevated sites across Wales appear positioned in locations that could support visual signaling. Fires, smoke, reflective surfaces, banners, or beacon systems could theoretically transmit messages from one hilltop to another. If a chain of observation stations existed, information might travel astonishing distances within minutes. Modern military historians have compared such systems to primitive telecommunications networks. Long before electricity, radio, or satellites, human societies developed methods for transmitting information using line-of-sight communication. Ancient Greece employed beacon chains. The Roman Empire utilized signal towers along frontier regions. Medieval kingdoms often maintained warning systems against invasion. The question is whether Myned y Garreg participated in a similar network. Unfortunately, physical evidence for communication systems is notoriously difficult to preserve. Fires leave limited traces, wooden signaling platforms disappear, and temporary equipment vanishes entirely. As a result, archaeologists are often left with geography rather than artifacts. The strategic positioning of towers suggests communication, but definitive proof remains elusive. At first glance, stone walls appear simple. Closer examination often reveals extraordinary craftsmanship. Every successful stone structure depends upon a delicate balance of weight distribution, friction, compression, and geometry. Modern structural engineers use mathematical models to predict how forces move through a building, while medieval builders relied on experience accumulated over generations. The survival of Myned y Garreg suggests that its builders understood these principles remarkably well. Even small errors in alignment can create weaknesses that eventually lead to collapse. Water infiltration, uneven settlement, or poorly distributed loads can accelerate failure. Yet numerous medieval towers across Britain have remained standing for hundreds of years despite exposure to severe weather. Researchers studying historical masonry frequently discover construction techniques that remain impressive even by modern standards. Some walls exhibit carefully calculated stone placement that maximizes stability while minimizing material requirements. Whether the builders consciously understood the underlying physics or simply inherited successful traditions remains unknown. Either way, the masonry of Mynyd y Garreg represents knowledge that was rarely written down and has largely disappeared from history. The visible tower may represent only a fraction of the original complex. Archaeologists increasingly recognize that many historic sites once included wooden buildings, defensive barriers, workshops, storage areas, animal enclosures, and access routes that have completely vanished. Stone survives, but wood rarely does. Modern LiDAR surveys have transformed archaeological research by revealing hidden features beneath vegetation and soil. In Britain alone, LiDAR has identified thousands of previously unknown earthworks and structural remains. This raises an intriguing possibility. The tower visible today may have functioned as the center of a much larger installation whose surrounding components disappeared centuries ago. If true, our understanding of the site may be based on only a small percentage of the original evidence. In the Nara Basin of central Japan, near the modern city of Sakurai, lies a massive earthwork unlike anything else from its time. Known as Hashihaka Kofun, the monument stretches approximately 280 meters in length and is widely considered one of the oldest large keyhole-shaped tombs ever constructed in Japan. Archaeologists began studying the mound in the late 19th and early 20th centuries, but its full secrets remain hidden. Because the site is regarded as a possible imperial tomb, extensive excavations have been restricted for decades. As a result, researchers can only investigate portions of the structure through limited surveys, aerial photography, geophysical studies, and small-scale archaeological work. This lack of direct access has transformed Hashihaka from a historical monument into one of East Asia's greatest engineering mysteries. The first mystery becomes obvious from the sky. Hashihaka belongs to a unique category of Japanese burial monuments known as Zenpo-koen Fun, or keyhole-shaped tombs. The structure combines a circular rear mound with a trapezoidal front platform, creating a shape that resembles a keyhole when viewed from above. Today, drones and satellites easily reveal the design, yet around the 3rd century AD, no technology existed that allowed builders to observe the monument from the air. The precision is remarkable, with the circular section maintaining a consistent curvature over a diameter exceeding 150 meters, while the rectangular section aligns almost perfectly with the main axis of the tomb. For comparison, many European earthworks from the same period were far smaller and often followed natural terrain rather than precise geometric planning. Hashihaka required surveyors capable of measuring large distances, establishing fixed reference points, and maintaining symmetry across an area covering several hectares. Researchers continue debating how these measurements were achieved. No surviving manuals explain the surveying techniques, no measuring instruments have been found, and no written records describe the planning process. The geometry exists, but the method does not. Modern estimates suggest that hundreds of thousands of cubic meters of earth were required to construct Hashihaka. Even conservative calculations indicate that the project involved moving enough soil to fill dozens of Olympic swimming pools. This immediately raises another question. How did 3rd century builders transport such enormous quantities of material without cranes, trucks, railways, or mechanized excavation equipment? Experimental archaeology demonstrates that moving a single cubic meter of compacted earth with hand tools can require hours of labor. Scaling that effort to the volume seen at Hashihaka suggests a workforce numbering in the thousands and a construction program lasting years. Yet the challenge extends beyond transportation. The mound is not simply a pile of dirt. Geological studies indicate that different layers were intentionally arranged and compacted, while the slopes were carefully engineered to remain stable despite centuries of rainfall, earthquakes, and seasonal weather changes. Modern geotechnical engineers recognize that improperly compacted earthworks often suffer catastrophic erosion. Hashihaka, however, has survived for nearly 17 centuries. The stability of the mound suggests a sophisticated understanding of soil behavior long before the development of modern engineering science. One of the least discussed mysteries involves the tomb's remarkable resistance to collapse. Earth structures naturally erode as rainwater cuts channels into exposed surfaces, gravity pulls material downhill, and seasonal temperature changes weaken the ground. Hashihaka should have suffered extensive degradation over time. Instead, much of its original form remains recognizable. Part of the explanation may lie in a technology known as fuhiishi, a protective covering of carefully placed stones that once covered portions of the mound. These stones function much like modern erosion control systems by reducing the speed of runoff, dispersing rainfall energy, and preventing soil from washing away. What fascinates engineers is that similar principles are used today in dam construction and slope stabilization projects. The builders clearly understood that water represented the greatest long-term threat to the monument. What remains unclear is how they developed that knowledge. No engineering texts survive, no technical traditions were recorded, yet the solution they implemented was surprisingly effective. Encircling Hashihaka is a large moat system. Traditionally, archaeologists viewed such moats as symbolic barriers separating the world of the living from the world of the dead. However, some researchers believe the moat may have served a practical engineering purpose as well. Large earthworks are highly vulnerable to groundwater pressure, as excess moisture can destabilize slopes, weaken foundations, and accelerate erosion. The moat may have functioned as a drainage system designed to regulate water levels around the mound. If this interpretation is correct, the builders possessed an understanding of hydrology far more advanced than commonly assumed. Comparable principles are employed in modern civil engineering, where drainage channels are routinely installed around embankments to prevent water accumulation and reduce structural stress. Hashihaka may represent one of the earliest examples of such thinking in Japanese history, yet direct evidence remains frustratingly limited because the tomb's interior cannot be fully investigated. The scale of Hashihaka creates another mystery. Construction on this level requires more than labor, it requires organization. Thousands of workers would have needed food, tools, transportation, supervision, and access to raw materials. Soil extraction sites had to be selected, stone resources had to be transported, and construction stages had to be coordinated. Modern project managers would recognize this as an immense logistical challenge. The tomb dates to a period associated with the emergence of the Yamato state, the political entity that would eventually become the foundation of Imperial Japan. Some historians argue that Hashihaka represents evidence of a powerful centralized government capable of mobilizing resources on an unprecedented scale. Others believe the project reflects cooperation among multiple regional groups. The mystery persists because the organizational system behind the construction has vanished entirely. The monument survives, but the bureaucracy that created it does not. Several researchers have suggested that the orientation of Hashihaka may not be accidental. Across the ancient world, monumental architecture was frequently linked to celestial observations. The pyramids of Egypt demonstrate extraordinary cardinal alignment. Certain European megalithic monuments correspond with solstices, and ancient Chinese royal tombs often followed cosmological principles. Hashihaka may belong to this tradition. Some studies indicate that its placement within the landscape and alignment relative to surrounding features could reflect deliberate planning connected to ritual or astronomical concepts. The challenge is determining whether these alignments were intentional or coincidental. Because the builders left no written explanation, every interpretation remains speculative. If astronomical planning was involved, it would imply a level of observational knowledge rarely associated with 3rd century Japan. Perhaps the most famous mystery concerns the identity of the individual buried inside. Many scholars have proposed that Hashihaka may be the tomb of Queen Himiko, the legendary ruler of Yamatai mentioned in Chinese historical records. According to the 3rd century Chinese chronicle Wei Zhi, Himiko governed a powerful kingdom and commanded significant political influence. The records describe her death and mention the construction of the large burial mound. The timing appears intriguing as radiocarbon dating of materials associated with Hashihaka places its construction near the period traditionally linked to Himiko's lifetime. Yet the evidence remains inconclusive. Without access to the central burial chamber, researchers cannot determine who lies within the mound. If Himiko is indeed buried there, Hashihaka could represent one of the most important royal tombs in East Asian history. If not, the identity of its occupant remains completely unknown. Most archaeological mysteries eventually yield answers through excavation. Hashihaka is different. The site remains under the protection of Japan's Imperial Household Agency, which restricts large-scale excavation because of its possible connection to the imperial lineage. As a result, modern researchers face an unusual situation. They possess advanced technologies including ground-penetrating radar, aerial LiDAR scanning, satellite imaging, and geophysical surveys, yet they still cannot fully investigate one of Japan's most important ancient monuments. This has created a paradox. Hashihaka may contain crucial information about the origins of the Japanese state, early engineering knowledge, political organization, religious practices, and royal burial traditions. But the very significance of the site prevents the investigations that might answer those questions.